with all of us after.
Yes, I already started the recording.
Okay, thank you. So, so today we will talk about deep learning, fundamentals of deep learning. So if you would like to start working on deep learning, so it should help you to start writing some code. So today we need to talk about fundamentals of deep learning. Of course, today, we've been using this figure a lot. So we have the artificial intelligence, which is the main umbrella, as you can see it here. And underneath artificial intelligence, we have small branch called machine learning. And from this machine learning, we have another maybe branch called deep learning. And in fact, today also inside deep learning, you can say that we have something called generative AI. So you can here say maybe generative AI, for example. So we have subset of deep learning called generative AI, which is nice area, and it's exciting because it is based on using large language models and transformers. So, but today we need to talk about artificial intelligence. What is AI, for example? So AI is broad area. It includes machine learning, deep learning, but also it includes many more approaches which don't involve any learning, right? Such as expert system. Did you hear about expert system before? In fact, expert system, it's a system which is not able to learn from data, but it can learn from human. And it's not learning, in fact, but we can use human experience to build an expert system which can make decisions, which can perform at the level of human intelligence. So, for example, if you have someone who is very clever for solving some problem, you have a banker, for example, and he can classify people based on some information into people who should get loan, people who should not get loan. So this classification problem or decision problem, it can be solved by human, and we can build an expert system which can replicate this process. To do this, there are two ways. The first way, we can build a rule-based system, and this rule-based system, it's the piece of information in the system is rules, and this rules, it's very simple. It's if then rule. So, for example, if the applicant has this income, then he can get a loan, for example, and so on. So, in a way, your knowledge or your expertise can be broken down into a number of rules, a number of if-then rules, and we just need to model those rules or implement those rules into our system. So we will have a rule-based, and this rule-based will consist of number of rules. This number of rules, it could be small number, it could be very large number. When the system is complex, it could be very, very large number. And we have inference engine. This inference engine will be able to use those rules, apply the rules to the input data, and it will find out which rules will be fired. And after that, it will combine contributions from each rule, and it will make some decisions. So this is an approach. We call it rule-based system. A rule-based system, it's like you can implement it today, for example, using fuzzy logic system, but there are many other software or platforms which are used for building expert systems. And maybe the other one called the case-based reasoning. So, for example, case-based, it's like if you have a doctor who make decisions to make a diagnosis for patient, we can call each patient will be a case. So for each case, we will have maybe description of symptoms, and the doctor, he will decide maybe the final diagnosis, for example, or prognosis. So we will have a number of cases. Maybe this doctor, he has a system in his clinic or in his hospital, for example, and they have those historical cases. So when he receives a case or a patient someday, he will write the symptoms, and based on those descriptions, he will also write, based on his diagnosis, he would write the diagnosis, for example. So we will have a case. So the case will consist of maybe a description and a label, which is a class label, or it will be classified into this kind of disease and so on. So the idea here also is to collect large number of cases and try to use those cases for building an expert system. And in this case, it will be case-based reasoning. So if you have a new case, the system will perform like this. If your system consists of maybe 10,000 cases, and you got a new patient, for example, and you want the system to diagnose this patient, you will feed the description of the patient or the case to the system, and the system will try to find similarity measure between the new case and all historical cases. So we can say that, okay, this case is very close to 2 cases. So chances that it will be diagnosed with the same disease will be much higher, right? So in this case, we can use those cases for helping us to make diagnosis. So in this case, we call it case-based reasoning. And case-based reasoning, it's nice because those cases are historical data and it's data effect. So you can say that, and it's also inference engine, but this inference engine, it will work with the cases rather than working with the rules. So if you want to build an expert system, you can go into one of those 2 directions, expert system based on rules or expert system based on cases. The advantage of building this expert system is that it's a transparent system. It's not black box. If you want to go for machine learning, for example, you know that it's a black box because when the model is complex, it's very difficult to say that to understand why this digit is 4 and not 3. It's complex. You cannot understand it from the machine learning model because I mean it's a successive layers and it's complex mapping between inputs and outputs. So it's very difficult to find out why this digit is 4, why this image is cat and not dog, right? Why the model decided that this one should be cat and not a dog, for example. So it's white box. So the expert system, it's white box because it has a tracking ability where it can trace back rules or cases which are fired. So you can just find, okay, this patient has been decided to has COVID, for example, because his case, because his temperature in this range, because the symptoms are in this and that. So in fact, you can trace back, you can find out which rules has been fired, and based on this information, you can understand why this patient has been classified as this and all that. So it has this tracing or tracking ability, which can give you a report. In fact, it can give you the decision. So this patient will be diagnosed as this, and you can get also explanation reports. This explanation report, it will explain to you why this patient has been classified as A and not B. So you can share this information with the patient, with his family, so people can understand. And the most important here also is physicians or doctors, because they want to know, I mean, if I need to use a system, I need to know what are the basis for making this decision. So usually in the medical field, but today, of course, the people don't care because, I mean, black box models also very, very smart and I mean, it's okay, right? But maybe before it was complex and people don't accept those black box models. And it was important to have a transparent intelligence or a systems with explanation. Today we have explainable AI, and in this explainable AI, we try to understand how the decision is made by the black box model. So artificial intelligence, it's a very large umbrella and it includes many areas. And underneath this artificial intelligence, we have the machine learning. And in machine learning, we know it, there are lots of machine learning. It's a field of study which gives computers the ability to learn without being explicitly programmed. So machine learning models, it learn from data, right? We learn, it learn from data. So it's not from human. So in the other side expert system, it was connected to human because I need to give those human expertise, break it down into a number of rules, build our system, or we need to collect the cases, solved cases, and we will match a new case, unsolved case against those solved cases. But in case of machine learning, it learns by exposing it to data. It should be exposed to data, and without any, it doesn't need any programming because it will just train by exposing it to data using some optimization algorithms, which will help us to adjust the weights to create this complex mapping between inputs and outputs. So deep learning deals with neural network with more than 2 layers. When we say that maybe there are 2 branches also here, we can say that there's shallow learning and deep learning. When it's shallow, it means our model maybe contains maybe maximum 1 hidden layer or 2 hidden layers. So in this case, we can say that it's shallow learning. When it's deep learning, we can say that in this case, we will deal with models or with neural network with more than 2 hidden layers. So compared to machine learning, deep learning can automatically extract features. When we are working with machine learning, as you can see, it's not very deep. Maybe it's 2 hidden layers, 3 hidden layers, but the input should be features, right? When it's just a neural network. When it's machine learning, for example. So we just need to feed the features to the input and make classifications. If you want to work with images, your model will be very, very complex, right? So if you want to feed your raw data to your machine learning model, it will be difficult because you need to make your model much larger, much complex to be able to create this complex mapping between inputs and outputs. And in this case, maybe each layer will try to find some representations of the input data. But in case of deep learning, it consists of 2 parts. The first part will be feature extraction, and the second part will be classification, which is the normal shallow learning models. So in deep learning models, we need to divide the model into 2 sections. The first section is the feature extraction part, and the second section will be a classification part. So the model will consist of 2 parts. So the machine learning model transforms its input data into meaningful outputs, and this process we call it learning by exposing to data, for example. And this data, it's known examples of inputs and outputs, so it should be labeled, right? When we talk about known examples of inputs and outputs, there are lots of inputs everywhere. I mean, lots of data everywhere. But the most important is that those data should be labeled. So it should be labeled. Otherwise, we need to use unsupervised learning. So what is the meaning of deep learning? So deep learning, in fact, it's a specific subfield of machine learning, and it tries to learn some representations from data using successive layers to achieve a meaningful representation. So if you have a model here like this one, this model consists of number of layers. So each layer will try to learn something from the data. It will try to learn something, some representations from the data, and it will deliver it to the second layer. The second layer, it will try to understand something else. So it will try to learn some maybe higher order representations and so on until you reach the output layer. And in this output layer, in fact, this layer, it will just use those information for classifying maybe the object into its predicted class, for example. So if we have the input image here, it's digit 4 from MNIST dataset, for example, we need to classify it into 4. So each layer will try to learn some representations from the data, and over iterations, I mean over time, we hope that those representations will make sense for our classification problem. So the deep here, it's not about deeper understanding, for example, which is achieved by this model, because the model cannot understand anything. In fact, it just create mapping between inputs and outputs. Rather, it stands for the idea of successive layers of representations using this literal layers stacked on top of each other. So we have this literal stack of layers, and each layer will try to learn some representation. And hopefully at the end, we will be able to classify this problem into one of those classes. So deep learning is technically a multi-stage way to learn the data representation. It's multi-stage way to learn the data representation using the successive layers. So, for example, I mean here, deep representations learned by classification model. So, for example, this is a model, and in this model, I mean the input to the model, it's MNIST dataset. It's one of the digits. I mean, you know, MNIST dataset has a dataset which consists of handwritten digits. And each digit, in fact, it's represented by a grayscale image of size 28 times 28 pixel values, right? So we will build a model. And as you can see here, this model consists of 4 layers. In fact, it's a 3 hidden layer and 1 output layer. So each layer will try to learn some representations from the input. So maybe this first one here, it's in the first iteration. So it will try to learn something, as you can see. And in the second iteration, it will try to refine it right? It will try to refine to try to understand or try to learn something which makes sense for our classification problems, and so on until your model converge. And in this stage, you can see that okay, the model now can learn something which makes sense for our model. So it's to try to learn higher order features automatically from the input space. And the output last hidden layer, we hope that this last hidden layer will have something which makes sense, right? And this information will be useful for classifying this input digits into digit 4, for example. So maybe this is digit, maybe this is, okay, this is the output effector from layer 4. So as you can see here, it's number of, maybe number of pixels, because it's 9, as you can see. So at the end, we will try to 0, 1, 2, maybe this one, 3, 4, 5, 6, 7, 9. So, I mean, anyway, we try to learn something which makes sense. When we send this one, when we send this high abstract representation to the output layer will be able to use this information for classifying our the input image into one of the classes. So now we will be able to predict it as 4. So the idea here is that all those successive layers will try to learn some higher order representations or abstract representations at the end, which can be used for the classification problem. So how this learning process will start, as we mentioned before, it's supervised learning. So it's very, very important to get a data which is labeled, which means the data set will consist of inputs and outputs. Inputs will be the input features, and the output will be the target feature. So it's very, very important to have these target features or true targets, because without this one, you will not be able to calculate this loss score. And the loss score is very, very important for the optimizer, because the optimizer will try to adjust the weights and the bias of my model in a way which will minimize this loss score. How can we calculate the loss score? It could be mean square error, for example. It could be the difference between the true target and the predictions. So first, I need to apply an input data, for example. It could be a vector, it could be an image, and those layers will try to learn some. It will do some data transformation, and it will each layer will try to learn some representations of the input, and finally we will have a prediction. Once we have this predicted class, we will subtract the true class from the predicted class, and we will calculate a loss value. We will send this loss value to the optimizer. This optimizer, it could be a stochastic gradient descent, for example. So this stochastic gradient descent, it will use this loss function for adjusting the weights and the bias. As you can remember from a perceptron, we used this rule. I mean, omega equal omega plus delta omega, and the delta omega, we need to adjust the delta omega, so it will be minus eta multiplied by the gradient, which is partial E by partial omega, correct? E, it is a gradient, in fact, right? Which is the loss gradient of the loss function, which we try to minimize. So it should be, maybe, for example, it could be something like this one. Target minus predicted square. So it could be something like this one. So we just need to solve this. The optimizer will try to solve it. And in this case, it will try to adjust the weights each iteration by just modifying it by adding delta omega. This is delta omega. It could be very small positive or small negative value, which will be used to adjust its weight and each weight and each bias. So it's very important to have a large amount of data, and this large amount of data, it should be labeled. If it's not labeled, we cannot use this approach. We need to find another approach, which is unsupervised, but we cannot use the same this approach here. So we talked last time about Keras. Keras is very important. So if we need to build a model to classify MNIST dataset in Keras, I need to build a feed-forward neural network. I mean, the equivalence of this one, in fact, in sklearn is SGD classifier, multi-layer perceptron, sorry, it's MLP. So I can build this one here in Keras, which is feed-forward neural network. But if you want to use, if you want to build it in sklearn, for example, I can just use MLP. multi-layer perceptron, MLP, multi-layer perceptron. So this multi-layer perceptron is feed-forward neural network. So now here we need to build it here in Keras. So we will use sequential EBI, and once you so model will be sequential, and after that you need to add your layers. So I will add the first hidden layer. This one will be my first hidden layer. So you can see here number of units here, it will be 512, which means this hidden layer, first hidden layer, it will has 512 neurons or perceptrons. You need to select also your activation function. I'm selecting here my activation function is ReLU. It's rectified linear unit. And in fact, we use rectified linear unit because it looks like this one, rectified linear unit, it looks like this one, right? So in fact, it's just if you want to write it in mathematical form, it will be max between 0 and x. So like y equal, for example, max of 0 and x, where x is the input, y is the output. And this function, as you can see here, it converts all negative values into 0, and all positive values will just convert it into the same value. So it will just provide, so it will pass all positive values, but it will convert all negative values into 0. So for example, if x equal -10, so y will be 0, because maximum between 0 and -10, it will be 0. And if x equals 10, so y will be maximum between 0 and 10, which will be 10. So all positive numbers will stay intact as it is, and all negative values will be converted into 0. So we build our model. So this one will be the first hidden layer. You can give it a name, maybe hidden layer 1, for example, if you have more hidden layers. And we need to define also the input shape. This is very important in this first hidden layer. We need to define the input shape. As I told you, we are in MNIST, and each image in MNIST is one grayscale image, which has 28 height, 28 width. So it's 28 times 28, right? 28 times 28 pixel values. And it's a grayscale, which means it's one channel, right? Give it a name. And, we have something called the dropout. It's also another layer. So I can just add another layer called the dropout. And the dropout, in fact, with this number, dropout coefficient or fraction. And the dropout, in fact, it's very important for it helps us to avoid overfitting. Sometimes the model is complex. The model contains large number of parameters, and we have very small set of data. And maybe in this case, if you will train the model for a longer time, it will be overtrained, and the model will overfit your data. And the overfitting means the model will will not be able to generalize. It will memorize your data, and it will not be able to generalize. So it will perform very well for the training data set, but it will not perform well for a new data set, for a test set, for example. So in fact, when your model is overfitting, you can discover it from the loss value. So you can find that the loss value for the training set was very, very low. So the accuracy is very, very high for the training set, but the accuracy is very, very low for the test set. So in this case, you can discover that your model overfitted your data. So to avoid this one, we can use something called dropout. And in dropout, in fact, as you can see here, if we want, I will just tell you the complexity of this problem. We use only one hidden layer, and this hidden layer has 512 neurons. And the size of inputs is 28 times 28. 28 times 28, it's 787 inputs. So when you multiply 28 by 28, you will get this number of pixels, 784. So if you want to find out how many weights for this layer, it would be 512 multiplied by 784, right? So number of weights in this layer. So it will be 512 multiplied by number of inputs, which is 28 times 28, which is 784. Not only this, in fact, sorry, this one, it's 512. So it will be 512 multiplied by 784 plus bias, because as you can see, a perceptron, I mean, I will just draw the layer like this one. It will be like this one. We have here number of inputs. Number of inputs, each input I will call it x1, x2 until xn. So x1, x2 until this is the number of pixels or pixel values until xn, which is x number 784, which means we have 784 inputs. And for number of units here, we are starting from 1, 2 until 512. When we make those connections, just make those connections. So it will be like this one. So we have here a matrix called omega, which is the weights of this layer. The size of this matrix will be what? It will be 512 times 784 values, different values. Plus, remember, we have here something called bias. Each one here is connected with a bias. So if we need to calculate total number of parameters of this layer, it will be 512 times 784 plus 512. If you can calculate this number, you will get this one, exactly this one. You can just try by your calculator, for example, multiply 512 times 784 plus 512, you will get this. You will get this number. So this number is very large. As you can see here, it's 401,000. It's around 402,000 weights, which is very, very large. So number of weights or number of parameters in this layer, it's very, very large, and it's a smart. Maybe this large number, it will. I mean, the model. We can say that the model has very large capacity, learning capacity, because number of weights is huge. So chances that this model will overfit is very, very high. To avoid this, we can use dropout. And this ratio here, 20%, it means in each iteration, we will drop 20% of this number. We will not train all this number each time, but we will train only 80% of it. And we will drop 20%. Right? So in the training process, when we started training our model, in each iteration, we will select only 80% of this number by random and adjust those weights. And in the next iteration, we will select another 80% and so on. So in this case, you can say we try to reduce model capacity or the capacity of this layer by 20%, because we will adjust only, in each iteration, we will adjust only 80%, not 100%, because we use the dropout equal 0.2. After this one, and as you can see here in this table, this dropout layer does not have any parameters, 0 parameters, because this one, it's just a dropout. It's not a layer, it's a layer, but it does not have any parameters. So it will just, we will use this one. I mean, number of inputs to this layer will be 512, number of outputs will be 512. So this dropout layer does not have any parameters. The number of parameters here equal 0. It will be just used for during the training process to ensure that this model will not overfit. And how can we select this number here, 0.2 or 0.3? It's hyperparameter. So if you are building your system using a pipeline, as we mentioned last time, for example, it would be smart, in fact, to use a grid search to select a good dropout ratio. It could be 0.2, 0.5, 0.3, we don't know. So it will be smart, in fact, to use grid search. So it can help you to select the best dropout ratio, for example. So this model is simple. It has only one hidden layer and one output layer. So we will get here one output layer. And when it is one output layer, it should have 10 outputs, right? It should classify into one of the 10 classes from 0 to 9, because in this dataset, we classify each image into one of those 10 classes, 0, 1, 2, until 9. We need to select. The input will be an image of a digit, handwritten digit, and we need to classify it into one of those 10 digits. So this model is simple. So we will have only one hidden layer and one output layer. So the output layer will have 10 units, 10 neurons. And because we need to classify into 10 classes. So the first one will classify into 0, the second will be 1 until we reach 9, right? The activation function here, we will use softmax. And when we use softmax activation function, we call this layer, in fact, softmax layer. So when we use in the output layer, when we use softmax layer, usually people call it output layer or softmax layer. And this softmax layer, in fact, it will calculate the probability for each class, for example. So each output here, it will be probability. So for example, if you have an input image, which is 4, so we will get a probability that this 4 is 0. It will be a very small number, of course. From 1, it will be also a very small number. 2, 3, 4. When it's 4, for example, so it will be a little bit higher number, and the rest will be small. So the summation of those probabilities should add to 1. So if we can say that we have 10 outputs, so the summation of OI for I from 1 to 10, this one should add to 1 because it's a probability. It should add to 1. So the output will be a vector, right? And there's a summation vector which consists of 10 values. So we will get just float numbers, and all those numbers are greater than 0 and less than 1. And the summation of all those values should add to 1. So for example, if you want to find maybe the final conclusion, maybe you need to use a function like argmax, for example. So we need to find the maximum. So the predicted label will be the label which has maximum probability. So now you need to give it also a name. You can call it output layer or softmax layer or whatever. It's nice to give it a name. And after finishing this, now we are finishing our model. So this is our model. So we build our model using sequential EBR. After doing this, we need to compile the model. And when you compile the model, you need to select an optimizer. You can select any optimizer, correct? And also the loss value or loss function. We will use categorical cross entropy because it's a multi-class classification problem. We can use categorical cross entropy. And the metrics which we need to maximize or minimize, here we will select accuracy, correct? We need to select accuracy. So in this case, we try to maximize accuracy. We have very nice function called model summary. So after doing this, there is a function called model summary. And when we run this model, it will give you this table, model summary. It will give you this table. And this table will summarize all model parameters. So as you can see, this has a number of layers, number of parameters of the only hidden layer which we have. I mean, the model consists of 3 layers here, as you can see, hidden layer, output layer, and dropout and output layer. Dropout does not have any parameters. Number of parameters here equals 0. Number of parameter of the output layer, it will be this number. Can you calculate this number? So the input to this layer, as you can see, is the output from the dropout, which is 512. So number of inputs which are going to this one will be 512. Number of outputs will be 10, or number of, this is the output shape. Number of outputs will be 10. So if you want to find the number of parameters, so it should be 10 multiplied by 512, right? Plus 10 bytes, because each one of those 10 has a bytes. So if you want to get this number, so it should be the weights of this layer. I can call it. We'll try. We will have those connections, correct? We will have those connections. So we can call it V, for example. What will be the size of V, for example? Weight matrix called V. So it will be 10 times 512 plus 10. So it will be 10 times 512 plus 10. So it will be 5,120 plus 10. So it will be 5,130. So it will be this number. From this table also, we have here something called the total parameters. And the total parameters here, in fact, it is a summation of those parameters. So it will be this number plus this number plus this number. We will get this total number of parameters. And after that, we have, this total number of parameters will be classified into 2 parts. One called trainable and the non-trainable parameters. And as you can see here, all parameters are trainable. We don't have any non-trainable parameters. We will get non-trainable parameters when we are working with transfer learning. So in transfer learning, for example, I can import a transformer which is used for image classification, or I can use a model like AlexNet, which is used for object detection and classification, for example. I need to transfer this model from its own application to my own application. So in this case, I will transfer this model or part of this model. Usually, we don't transfer the whole model. We transfer the feature extraction part, because we agreed that in deep learning, the model will consist of two sections, one called feature extraction and one called classification. So when we talk about AlexNet, maybe we are not interested in, because AlexNet is used to classify each image or each object into one of 1,000 objects. It has been trained to do this. So if you have an image with a computer, mouse, keyboard, it will classify into those objects. But maybe my application does not include this one, but it is images, and it's about object classification. So it's the same application, right? So in this case, I can transfer this model from its own application to my own application. Maybe my own problem, I need to classify into 5 objects, not 1,000. And I don't care about the other 1,000 objects. I need to classify into one of the 5 objects. And I have a small data set, which I need to use to train my model. So in this case, maybe I can just go to AlexNet. So I can import AlexNet, and I can import only the feature extraction part, which is the most important and it's most time-consuming or computationally demanding part for in the learning process. It requires large amount of data, and it requires high computational resources to train. Because in AlexNet, it has been trained using 60 million, I guess, 60 million images, which is very, very large. I don't have access to this amount of data. Maybe I have only 200 images, or maybe 1,000 image. So I cannot use those small number of images for training a whole model. My model will overfit. To avoid this problem, I can just import AlexNet, and I can use the feature extraction part, only the feature extraction part. I will import it to my application, and I will modify the classification part. So now my model will consist of 2 parts. Feature extraction, which contains maybe about 60 million parameters, and I will add a layer for classification, or 2 layers for classification. My classifier, it's brand new, so I need to train it. So in this case, I can build my model like this, and I can freeze the feature extraction part, because this one has been already trained. So I will freeze that part. So when we freeze it, we will see that number of parameters here in non-trainable. We will see this number here. So number of parameters of the feature extraction, it will appear here in non-trainable parameters, right? And in the trainable parameters, it will be the parameters which will be trained, which will be the parameters of the new sections which has been added to your model. Those 2 layers for classification. So the classifier, it will be the parameters of the classifier. So in this case, in fact, you will divide your parameters into trainable and non-trainable, and you will use the limited amount of data which you have for training the non-trainable parameters. So in this case, we will be able to see trainable and non-trainable. So this is the model summary. So you will get this table, you will get all those details. We have also a nice function called the plot model, as you can see here. And in fact, this plot model, it will plot this one. Maybe it's okay. Maybe you can add it to your thesis, to your something, publication, for example. Maybe it's useful, maybe it's not, but it will give people more details about the models, number of inputs, number of outputs of each model, and number of layers, and names of layers. So the input to this function will be your model, because we are building something called model. So the input to this function will be model. And also you can save it to a file. You need to select maybe the extension .png, .gpg, for example. Maybe show shapes true, show layer names true. You can decide here also. I mean, you need to go into this function and try to see. Now I'm just selecting here show shape and the show layer names. Maybe you can show also, you can make it more complex, and you can, maybe this is by default, right? So please try to dig into this function and try to look into all options. Maybe we can use it to see more details and more information. So it will plot your model and it will save it in this file, right, with this extension. After training your model, in the training process, we agreed that we need to split my data into training part and testing part. We will use the training part for training our model. And after finishing the training process, we will test it against the test set, which is the brand new data. We hold out the test set for testing our model. We will use a test set and we will test the model. And maybe we can use confusion matrix to show you the results to show the accuracy of your model. Confusion matrix, it's very important when you are working with classification problems, but also there are many other methods. You can get something called the classification report. And in this classification report, it will give you very important numbers, such as accuracy, precision, recall, F1 score, and so on. If you want to get those numbers, you have very simple command called classification report, and it's from sklearn, as I remember. You will use it and you will get all those numbers. So now we trained our model. We got here this confusion matrix for the test set. And as you can see here, the most important in the confusion matrix is this diagonal, right? We need to maximize numbers across this diagonal because those are the true positive, right? True positive or true negative. Anyway, it's the true classes, right? True classes. So this one means we have 971 0 correctly classified as 0, right? This one, for example, it's 1000, maybe 3 classified as 3. So this is the true values, in fact, the true classes. So we need to maximize numbers across this diagonal, and we need to minimize other numbers because other numbers means the model is confused, which means here, for example, this one. So the model here is about this 10. Maybe it's this 10. It's 10, 2 misclassified as 8. Maybe people are writing 2 and 8 close to each other. So we have here the model is confused in 10 cases. So this one means the 10 digits 2 were misclassified as digit 8. So the model is confused. So if you want to build a model which has better accuracy, we need to maximize numbers across this main diagonal and minimize all other numbers. Sometimes people are curious to see the intermediate values. So if you want to see the intermediate values from your model, so I trained my model here, and maybe I'm curious. I need to see how the output, the output from this hidden layer, how it looks like, right? When we are building our model in a sequential approach using sequential API, it's impossible to get access to those values because the model is a sequence of layers. And the output from one layer, we will feed it into the other layer, next layer, and so on, until we make a conclusion or classification. But if you want to see the intermediate values, so you need to see some values from some layers, for example. This hidden layer, I need to see the output from this hidden layer, which will be 512 values, correct? I mean, the output from this layer will be 512 values. I need to see, because the input image is 28 times 28. So for each image, if this digit was 4, I need to see, because this layer should learn some representations from my data. So I need to see really, what will be the output from this layer, how it looks like, right? For number of digits, I need to test it with maybe 4, with maybe 0, with 1, and I need to see, is there any connection? How it looks like. So in this case, we need to use something called the model API. And this model API, it will help you to build more customized models. And it will help you to get access to some of those intermediate values. So I can just define a temp model. This temp model, I will use it to get access to the output from this hidden layer. So it's very easy. Temp model equal model. the input to this model, it will be inputs and outputs, right? So I just need to define inputs, and you need to define outputs. The inputs, it will be the inputs to my original model. So it will be model.input, this one. And the outputs, you need to decide it, from which layer you want to see the output or plot the output. So I need to get the output from the hidden layer, for example. So it will be just model.get layer. You need to select here, you need to write here the layer name, which is hidden layer, for example, or number. It could be name or number, right? So dot output. So in this case, I'm building this temp model, and the input to this model will be the input to my original model. The output will be the output from layer number 0 or layer number 1 or layer number 2, correct? Or from this hidden layer. So now I defined a temp model. It's after training the other model. So after doing this, I will just use this temp model for prediction. I will send some images. I will send some images to this model, temp model, and I will use it for predict, correct? So it will be temp model.predict, and this one will be the input. I will send some test images, for example, from 0 to 10 in random, because it's shuffled. So it will be maybe I will send 7, I will send 2, I will send 1, 0, 4, maybe 1 again, 4, 9, right? I don't know this one. Maybe it's 6, it looks like, I don't know, and the 9 again, correct? So in this case, when I send 7 to my temp model, I will get the output. What will be the output? Temp output. The output will be the output from this hidden layer. So it will be this image. Right? This one, in fact, it's 512 pixel values. It's feature map, which has a size of 512. If you want to plot it using image show, for example, you just need to reshape it, because I need to plot it as an image. 512, it's 32 times 16. So just reshape it to 300 as a matrix, or as an image of a shape of 332 times 16, right? 32 height and 16 width, and I will just display it. So it will be like this one. So when we feed 7, we will get from this hidden layer, we will get this output. When you feed 2, you will get something similar. I mean, there is no difference. In fact, it's more or less the same. When you feed 1, you will get this one. When you feed 0, you will get this one. 4, you will get this one. So you can just imagine that when you have an input 72105 in the numbers, you will get something like this one, right? Of course, there is some difference. As you can see here, this is 4, this is 9. You can see that it's different, in fact, right? There is some difference. I mean, white pixels will be, the white pixels will be maybe 1, and the zeros, black pixels will be zeros, correct? So I mean, the dark, when it's dark, it's close to 0. When it's bright, it's close to 1. So you can see, I mean, the difference here, we have some bright locations, and so it's a little bit different. So in fact, each feature map will be different for each input. But this is a representation which the model is learning from the data. I mean, this hidden layer, the only hidden layer which we have, has been learning those representations of my input data. So now I try to display, I mean, make this display the inputs and display the output from this hidden layer, and at the end try to display also your model output.
A question.
So, yes.
Why do you change the shape?
No, it's just by I need to use image show, because this one, those
Yes.
512, in fact, it's 1D vector, right? Those 512 from the model, it's one vector. One large vector has a size of 512 values. So some values will be zeros, maybe some ones, maybe numbers are 0.5, 0.9. So it will be just one large 1D vector. It's 1D vector.
Yes, I understand that, but the original picture is 28 times 28.
Yes, this
and
one.
then,
It's
and then we can understand it. Why then?
Yes.
Next, the encoded image. Why 3216? Why not use the same 2828? Is there a
No? Yeah, because 20. I mean, this intermediate output has a size of 512. And 512, it cannot be 28 times 28, but it can be 32 times 16. Can you multiply it?
Yeah, it's 512. Yeah.
Yeah, so it's 512. So in a number, because I need to display it as in a small space, I can display it as a vector. So this one is a vector. This one, it's 10 times 1. Correct? So in
Yeah.
fact, I can display this one as a vector, like 1 times 512 or 512 times 1, but it will be something very, very large. It will be like this one. It will not be convenient to put it in a small space.
Yeah.
So I just try to reshape it so I can display it as an image.
Okay.
Yes. What was your next question?
No, that was it. That was it.
Okay. Yeah. So it's just to try to find good numbers, good combination of numbers. So you can just display it as an image instead of displaying it as a very large vector. But at the end, it will be a vector of numbers. Maybe it contains many zeros because it's almost black everywhere, and some maybe bright pixels, which is 1. This one, it's clear that this one are 1 and the rest are zeros. But then you can see that there are some gray pixels. Those gray pixels, it will be number between 0 and 1. So instead of displaying it as one vector, I try to reshape it into an image. So 512, you need to find maybe 2 numbers. So when you're selecting 512, it's smart to select a number which can be factorized into 32 times 16 or anyway, right? So now we are displaying the image. This is the input image, as you can see here. I'm displaying here the test set. And the test set, in fact, in the MNIST data set, it's one vector, which has a size of, it's 1D vector also, so I need to reshape it again into 28 times 28, because in the data set, when you download the data set, it will not be an image, in fact, it will be just one vector of size 786 something, which is 28 times 28. So you need to reshape it into 28 times 28 to display it like this one. So now this part will display the input image. This part will display the encoded image. So this is the output from the first hidden layer. So it will be temp output, right? It will be temp output dot reshape. So this one will be the encoded image of fisherman, for example. And also I need to display the prediction, the output, which is y predict. So this is y predict, it is the output from my model, right? So it will be y predict and reshape it to the, 10 times 1 or 1 times 10. I want to put it like this one so I don't take large space from my slide. But if you want to represent it in a different way, you can just do it. So in this case, we trained a model and we trained it for classifying MNIST. And in fact, we can achieve a very good accuracy using this model. This is the code. So if you want to, in GitHub, you can just click this one and try to test this code, try to make changes if you would like to. And of course, when you click this one here, you will see the confusion matrix, you will see the classification report in details. So there are some details which are in the code, but it's not here in the slide. So if we need to, data is very important in deep learning. Data is very, very important, and it's very important to have the data in the correct format for the neural network. So we need to talk about data representation for neural network. So we need to talk about data batches. As I told you, if you will use, for example, stochastic gradient descent, in stochastic gradient descent, we will train the model one time each iteration. We will train the model one time for each example. It's called online learning. So if you have, for example, in stochastic gradient descent, if you have 100 data points and you will train your model for 10 epoch. So what will happen? In fact, in each epoch, we will train the model 100 times, one time for each data point. So this is the stochastic gradient descent. In batch gradient descent, we will put the whole data into a large batch. This batch will consist of 100 points. We will calculate the gradient for those 100 points each iteration, and we will calculate the mean gradient, and we will adjust the weight only one time each batch. So if you will train your model for 10 epoch, So in this case, we will train the model only 10 times, 1 time for each batch. In batch gradient descent, we call it batch gradient descent. There is a trade-off between the stochastic gradient descent and the batch gradient descent, and we call it mini batch gradient. And in this mini batch gradient, we need to divide our data set into a number of batches, and the size of each batch, in fact, it will be based on the memory which we have in our computer. And the size of the data. If you are working with videos, maybe it will take too much memory space in your GPU, for example. And in this case, you cannot use batch gradient because you don't have enough memory to hold all your data set at the same time. So in this case, we need to divide our data into a number of batches. The size of the batch, the batch size or number of videos or examples in each batch, or the size of the batch, it will be decided based on your memory and the size of your each example, for example. So you can calculate it. So for example, if you have 32 gigabytes RAM, for example, so in this case, the model size, we can calculate the model size because we know the number of parameters. So if we can go back here to this model, we know that this model consists of 407,000 parameters. So if you want to calculate the model size here, you just need to multiply this number maybe by 3 if it's a float number, each weight will be float number. You just need to multiply this number by maybe 3 bytes, correct? Divide it by 1,124. Is it correct? To convert it into kilos and convert it again into maybe megabytes, kilobytes, megabytes, and gigabytes. So you can calculate, in fact, the model size. If you are using a large model, you can calculate the model size. And also for your data set, you will look into your data set, for example, and you will decide, what will be the batch size based on the size of each example of the training data set. So maybe if I'm working with videos and each video has a size of maybe, for example, 20 kilo, 1 megabytes, correct? If it's 1 megabytes, each example. And my memory is maybe 32 megabytes. And maybe my model size is maybe 10 megabytes, correct? So in this case, in fact, and I have a lot of data sets, and each example has a size of 1 megabytes. So maybe in this case, maybe I need to have the batch size. It should maybe equal maybe 10 or maybe 16, for example, 16 examples, because 16s will be converted into 16 megabytes. So 16 megabytes plus 10 megabytes, it will be maybe 26 megabytes. So maybe this is enough. It will be okay for my training process. I cannot use batch gradient because batch gradient, I need to hold all my data sets in maybe my RAM, for example, so it will be very difficult for my computer. So in this case, I need to reduce the batch size. So in this case, we need to divide the data set into a number of batches, right? So it's according to the memory, your memory available for you, maybe the size of your each training example. So you will decide batch size, and based on the batch size, you will get number of batches, right? Because if each batch size will consist of 16 and I have, for example, 100, so it will be 100 data points divided by 16, we will get number of batches, right? Of course, some batches, not all batches will be 16, maybe example, maybe some batches will be 10, right? Maybe the last batch, it will be small or less. More, it will be less, it cannot be higher than 16, for example. So we just here, we need to just talk quickly about time series data and or sequential data, for example. When time matters, time series is stored in a 3D tensor with an explicit time axis. When time is important, we need to consider time. We cannot ignore time coefficient. So in this case, we need to store our data into a 3D tensor. The data set of stock prices, for example, just as an example, we have a data set of stock prices. So every minute we store the current price. We have the current price, we have the highest, and we have the lowest price in the past minute. So each minute we need to have a record of maybe the current price, the highest, and the lowest price each minute. And in fact, each hour consists of 60 minutes, and in the maybe working day consists of maybe 6.5 hours. So each minute is encoded in a 3D vector. So the entire day of trading will be 6.5 hours times 60 minutes. So we should expect that we should have 390 data points. So each day we will store 300. This one will be the data set. I mean the number of features. We have 3 features because we need to store the current price, maybe highest price, and lowest price. So the last dimension here will be the number of features, and this one will be number of samples, correct, per day. So each day we need to store 390 data points. And in a year, for example, we have 250 working days. I mean, just to remove holidays and vacations and so on, weekends. So we should have in a year 250 days, working days, where you can make trading. So in this case, in a year we will have 250. So in this case, if you want to use a data for 1 year, it will be like this one: 250, the first dimension, 250 days. The second dimension, it will be a number of samples. It will be 390, and the third dimension will be a number of features. If you want to store data for maybe 10 years, maybe in this case we need to store it in a 4D tensor. So here we will have 10, right? Number of years, for example. So in this case, you can organize your data set, and in this case, we will consider time. So the data set, this is one example. Another example of tweets, for example, where each tweet is a sequence of 280. I mean, Twitter before, now X, I have no idea if X has the same restriction, but before, when it was Twitter, when you tweet, each tweet size should be maximum 280 characters, right? So 280 maximums. So if you need to tweet, it should be below this number or equal, correct number of characters. And in fact, they do it like this to be organized, to be compact, to be easy to store it and use it for machine learning. Because in fact, when you tweet, they use data analytics and they try to find trends. They try to collect lots of information from those tweets from all over the world. So they can find out if people in a country, they are happy, they are sad, what is the trend in this country, what is going on. So they can use machine learning and data analytics for analyzing this one. So when it is 280 characters, it will make life much easier, right? It will make things much, much easier because when we try to encode it, for example, so we have 280 characters. Each character will be one of those alphabet 128 unique characters, alphabetical characters. Each one, it should be one of those. So usually we have 128 unique characters. So it will be like very large vector of zeros, and it will be just one in some location as the index of this character. So maybe because this character is A capital, for example, so maybe it will be 1 here and zeros everywhere. If it is B, it will be 1 here and zeros everywhere. So in this case, each tweet will be encoded into a vector of 280 characters, comma, the second one will be a number of characters, number of unique characters, comma, 128. Right? So each tweet, when you write a tweet in Twitter before, now it's X. So it will be encoded into a 2D tensor. It will be encoded as a 2D tensor of shape 280, comma, 128. It will be like this one. But it will be sparsely tensor. I mean, it will be zeros everywhere except little ones, except 280 ones somewhere. So it's not, maybe this is not the best way for storing it because it will consume too much memory, in fact, and it's not efficient. Maybe you can use word embedding for storing it. It will be much better. So anyway, each tweet will be encoded as a data tensor of this shape. If you have a data set which consists of 1 million tweets, in this case, we need to add a third dimension. This third dimension will be number of samples. So now this one, it is the number of samples, comma, 280. This is number of characters, and each character will be encoded into this unique characters, one of the 128 unique characters. So it will be like this one. So this is how we will encode those sequential data, for example. So it will be like maybe time steps. It will be time steps times samples, number of samples, times number of features. It will be like this one. So here, for example, those 1 million tweets. So maybe this one will be the time steps times number of samples. No, this one, in fact, it's maybe this one, it's a number of samples, comma, 280, which will be maybe this is maybe 280. Maybe this is number of samples. Is this one number of features, for example, or number of characters, comma, how we will encode each character. So each character will be encoded in a vector of 128 unique characters. If you are working with images, for example, images usually have 3 dimensions. It's height, width, and color depth. When it's MNIST dataset, it was grayscale. So in fact, it was only one channel, right? So this one was 28 height times 28 width. And the width here, in fact, it's only one because it was grayscale image. It was grayscale. But if you are working with RGB, so RGB will be represented as this one. So we will have this one RGB. So it will be one red, one green channel. It will be like this one, and also a blue one. So it will be height time width time number of channels, which will be 3. So grayscale images has one-dimensional color, similar to MNIST dataset, for example. So a batch of 128 grayscale images of size 28 times 28, it will be encoded times this one. It will be 4D tensor. So the first one will be 128, which is the height. No, sorry, this is number of samples. This one is number of samples. And each sample will be encoded as a 3D tensor. So the 3D tensor, it will consist of height, width, and depth, which is the number of color channels. So the standard format will be samples times height times width times color depth. This is RGB. If you are working with video data, so it will require, I mean, this RGB, it requires 4D tensor. 4D tensor. If you are working with video, you just need to increase the dimension by 1, which is number of frames. So you will have the number of samples, correct? Maybe you have 10 videos. And each video consists of number of frames. Each video, maybe this video, the sample here, it will be 1 second or 2 seconds. And in each second, for example, we have 24 frames. So we can just talk about this example here. So anyway, the sample here will be number of seconds because it's a video. Maybe it could be like this example here, it will be 4 seconds. It will be 4 seconds. And in each second, in fact, we have 24. We have 60. We have 60 frames per second. Maybe it's too much. No problem. So in this case, number of frames will be 4 times number of frames per second. If you have 60 frames per second or 24 frames per second, so number of frames will be number of seconds multiplied number of frames per second. So now we will get number of frames. And in fact, each frame, it's one RGB image. So each frame is a single image, single RGB image. So this image will be represented as height, width, and color depth. So we have this example here. We have 60-second YouTube videos, and each YouTube is 144 times 256. So 144 is height, 256 is width, and those video clips are sampled at 4 samples per second. We have 4 samples per second. 4 samples per second. It's 60 seconds. We have 60 seconds, right? 60 seconds. And each second, in fact, has four frames per second. Slow resolution, in fact. So number of frames per second here, it's 4. So it will be, number of frames will be 60 times 4. 60 times 4, you will get 240 frames. So the first dimension will be number of samples. We have 4 samples. Number of samples. and each sample has a number of frames. It will be 240. This 240, it's 60 seconds multiplied by number of frames per second. So it will be 60 times 4, it will be 204. And in fact, each frame is RGB image. Each RGB image, it will be encoded in 3D tensor of height times width times depth. It will be like this one. So if you want to find the size of this, if you want to find the size of this patch, how can we find it? Just multiply all those numbers. 4 times 240 times 144 times 256 times 3. Just multiply all those numbers together. You will get number of values or number of pixels, in fact. Multiplying all those numbers together, you will get number of pixels. And if you store each pixel value in 32 bits, if it's a float 32, for example, 32 bits, which is 4 bytes, right? So then it will require this number multiplied by 32 bits divided by 8. So you can get number of bits. You can get number of bytes. Sorry, when you divide by 8, you will get number of bytes. Divide it by 1024, you will get number of kilos. Divide it again by the same number, you will get number of maybe megabytes. So it will be 425 megabytes. So if you want to store this, if you want to store this patch, it requires 425 megabytes, which is okay. But this is how we do it. So in fact, when you are working, you can calculate the size of your model, and you can calculate the size of your batch, and you can decide which learning mode you will use. If you will go for stochastic gradient descent, batch gradient descent, or mini batch gradient descent. So now we are talking about images, videos. I want to talk about text data, and we can take an example here, which is IMDb dataset. And IMDb, it stands for Internet Movie Database. Internet Movie Database, it's something like Netflix, right? You use it for for classifying. I mean, classifying those movies. I mean, some people, they like a movie, some people don't like it. So in fact, they can write recommendations or review. You can use those reviews to calculate a score for those movies. So some movies, for example, it can take a high score and low score, and in fact, it's based on those positive and negative reviews. So maybe they have an equation for calculating this score. I don't know how they do it, but it could be something like number of positives divided by total number of reviews, right? So for example, if there is a movie, for example, and this movie got maybe 1,000 reviews, correct? And those reviews, maybe 600 are positive, 600,000 are 600 are positive, 400 are negative. So in this case, you can just say maybe the score of this movie will be 6 divided by 10, so it will be 0.6. Right? We multiply this one by 10, so it will be just 6. Right? So when you are watching movies, you can see this number. So usually they calculate this number based on the feedback which they will get from people, from audience. So and this feedback, in fact, it's just a review. So people will just write a review, and it should be classified if this one is positive or negative. We call it sentiment analysis. So this process, in fact, or this problem, we call it sentiment analysis. So people will just write something, and you need to say, okay, this one is negative, this one is positive. Of course, you can do it manually, so you can hire people, and those people will read those reviews, and they will classify them, this one negative, this one negative, this one positive. Correct? So you can do it like this one. But it's, of course, if you want to do this process manually, it will be very, very time consuming, and it will cost money, and it will take time. But of course, it's a problem which can be automated using machine learning. So In this problem, we have this IMDb dataset, and this dataset consists of 50K movie reviews for natural language processing. Natural language processing because it is written using our natural language. And it is used for text analytics and for binary, maybe sentiment classification. So I can use it for classifying the movies. This movie is positive, this movie is negative. So you can use this one for sentiment analysis. So this dataset consists of 50K movie reviews, 50,000 reviews. Each review is a sequence of words of different lengths converted into a sequence of integers, where each integer stands for a specific word in a dictionary. We select the top 10,000 most popular words. I mean, we need to encode it for machine learning. Machine learning cannot understand the text. So here in this movie, in fact, they did this. They collected those reviews, for example. It was labeled, 50,000 was labeled, maybe manually, correct? Maybe they asked people to read and they finished it in maybe 1 week or something, reading those reviews and they classify it into negative or positive. So now we have a database which is labeled the data set. For example, we have input features, which is text, and the output, which is sentiment analysis or sentiment classes, negative and positive. So it's a binary classification problem. So you will classify each review into positive and negative. So it's binary classification problem. To encode it, of course, we can use something similar to Twitter, for example. So we can say that, okay, but we need to decide the size. I mean, because for machine learning, we cannot use this. We cannot use unlimited. I mean, the size should be limited. I mean, should be known, in fact. But in fact, those reviews, some reviews are long, some reviews are short. So to fix this problem, after collecting all those reviews, they selected the top 10,000 most popular words. They created a dictionary of the top 10,000 most popular words, which are used here. We can use it. We can do this by statistical approach. So I can find the most, the frequency of the words, which word has been used more, and we will sort it from high to low based on the frequency. So, so they did that, and they want to simplify the data set. So we will encode each review into those 10,000. We will limit it to into those top 10,000 most popular words. So which means we will create a vector, very large vector, which consists of 10,000 values. So starting from maybe 1 until 10,000 words. And we will have here index, correct? And it will be filled by zeros. This vector will be filled by zeros, and we will look into the first review, for example. We will escape words which are not in the list, and we will pick only words which are in the list. So, for example, if this word is in the list, big, for example, we will put one here in that index, the index of big. Maybe this word that exists enjoyed. Maybe this one is in the list. So in this case, we will put one in the vector, in the same index, and so on. So in this case, in fact, we will encode each review into a vector of 10,000 values. And because we have 50,000 reviews, so finally the data set will be represented as a 2D tensor, correct? The first dimension will be number of samples, and the second dimension will be number of features, because now we have 50,000 reviews, and each review will be encoded as a vector of 10,000 values, like this one. So it will be, so each review or the data set will be represented in this way. So it will be 50,000 times 10,000 values, right? Those reviews are divided into 25,000 for training. It's divided already 25,000 for training and 25,000 for testing. So it's balanced, in fact. Each set consists of 50,000 positive reviews and 50,000 negative reviews. So it's very, very good. So the data set is divided into 1/2 for training and 1 half for testing. And in fact, each half is further divided into 50% positive, 50% negative. This one also 50% positive, 50% negative reviews. So now if we need to train a machine learning model for sentiment analysis, we can just use this data set, and we will train the model using the 25,000, and we will test it with a second 25,000 and check the performance of our model. If you want to get the data, you can download it from here, from Kaggle. So if you want to load INDB dataset, in fact, also you don't need to get it from here because you can get it from keras.datasets. You can import it from keras.datasets.indb, load data, and also you need to use this function, which is get word index. Get word index. When we load the data, you need to define the dictionary. So number of words will be 10,000. So now we are defining our dictionary. We will limit our dictionary to 10,000. Of course, when you do this, you limit yourself, you lose some information because we are keeping some words. I don't know if those words will make sense or not, right? It might maybe destroy the meaning of, but we try to pick positive words and negative words. I mean, in this problem here, in fact, we are not focusing in the context because maybe some people are writing in a complex way. So maybe he will use negative words which looks negative, but the main conclusion will be positive or vice versa. So now anyway, here we are limiting ourselves to 10,000 words. We will ignore maybe words which are not popular. So each review will be restricted to this vector of size 10,000, most frequent or most occurring words. So it's 10,000 dimensional vector of zeros except for word indexes. So it will be like this one. So I mean the result here, we will get the X train, Y train. You need to vectorize it to see how it looks like. So result will be NP0, length of sequences multiplied by number of words. Number of words equal 10,000. Length of sequence, so maybe each review for I sequence and enumerate. So you will get if this word exists in that, if this word exists in the sequence, right, you will put 1. So it will be zeros. I mean, this vector, it will be zeros of size 10,000. It will be 10,000 times length of sequences. So this one, in fact, it will be like something 5,000, 50,000, comma, 10,000. It will be like this one. And we will enumerate each words in the sequence, for example. And if this word exists in the dictionary, we will put 1 at that index. So we will have here X train and X test. And I mean, it will be just numbers. You can convert those numbers to be as a float 32, for example, so you can calculate the size. So if you want to calculate the size of this, I mean, data set now, it will be 50,000 times 10,000, maybe times 32 bits divided by 2, maybe divided by 124. You can get the size as in kilobytes, for example, in this case, and so on. So Y train and Y test, it's binary classification problem. Maybe you need to use this function to categorical. So I can, because it's just each Y here will be like positive, negative. It will be zeros, ones, something like this one. When we use this function, we convert it into 2D, into one-hot encoding. So it will be this one 0 here. So it will be 1, 0, 1, 0. It will be 0, 1, 0, 1. It will be something like this one. So in this case, we will use one-hot encoding to convert categorical variable into one-hot encoding. And in this case, when we are building our model, we can use in the output layer, we should have 2 outputs, right? We can use 2 outputs. So and also we can use softmax activation function here in the output layer. So maybe if this number is 0.8, this number is it should be 0.2, for example, summation add to 1, because we use softmax activation function. So maybe when this one is larger, this one will be classified as positive. Maybe this one will be classified, and so on. right? So it can be like this one. So it could be, for example, maybe 0 when it's positive, or 1 when it's positive, review, and 0 when it's negative, review. So it could be done like this one. So this is just an example. This is a sequence of words. This is a sequence, and as you can see, it's long, consists of many words. We will convert this one into a 10,000 we will convert this one into word indices. We have a dictionary. We agreed that the dictionary consists of 10,000. So we will just go to those words which exist in the dictionary, and we will replace it with the index, correct? And we will skip things which are not in the dictionary. So at the end, we will convert this one into a sequence of integers, right? And after that, maybe, I mean, this step, maybe it's not very important. We will go to this 10,000. This one will be a vector of 10,000 values, right? And we will go to this one. It's the first word in the dictionary, maybe word number 1, not 0. So we will put 1 here in the index 1. We have 2. Maybe this is 0, 1, 2. We need to search for 2 if we have 2 here. Yes, we have here 2, so we will put here 1. Do we have 3? I don't think that we have 3, because here it will be 0. We don't have any 3 here. If you can look into it, we don't have any 3. Correct? Yes. We will go to check 4. Yes, we have 4 here. So we will have 4. So this one will be 4. Do we have 5? We should have 5. Yes, we have 5 here, so we will get 5. We have 6, and so on. So in this case, we have many 5, in fact. So in fact, in this approach, we don't count for repetition also. So when word is repeated several times, we have 6 here. So when the word is repeated several times, we don't count it. We just count it only one time. So and so on. So as you can see here, this vector, it will be just a vector of zeros everywhere except some ones at the index of the word, which exist in the sequence of words and the sequence of integers. And the rest will be zeros. So maybe this is not very efficient for machine learning, because when we feed this one, it's like word embedding. In fact, when we feed this one to my model, most of the inputs will be zeros, correct? Except little ones, according to the size of my review, right? So if you need to build a model for sentiment classification, it's the same. We will use sequential API, and also you will just select a number of layers. So we selected here the one hidden layer. The input shape would be 10,000. As you can see, we will use activation ReLU. It's ReLU because those numbers we don't have any negative numbers, right? All numbers are just 0 and positive. So it's safe to use ReLU. Number of, it will be dense layer. Number of units will be 1024, right? 1024. It will be followed by dropout, because this large number, it's a very, very large number of weights. I mean, the weights here, it will be this number multiplied by this number. So you see this number, it's very large. 1, 2, 3. It's a very, very large number. It's 10 million, correct? It's 10 million, 241 parameters, 241,000. So it's a very, very large number of parameters. So I mean, this large number of parameters, its chances to overfit will be very, very high, in fact. So it's very important to use dropout with very large fraction, right? Dropout coefficient, it should be very, very high. Then we will use another maybe hidden layer, followed by dropout, another hidden layer, followed by dropout, and finally another also hidden layer, and finally we will have this output layer. I'm using here sigmoid, not softmax. Number of outputs will be 2, because it's a binary classification problem. We will compile the model. When you compile your model, you need to decide your optimizer, the loss function, how we will calculate it. We will use binary cross entropy, because it's a binary classification problem. The metrics which we need to report is accuracy. And we can use model summary and model plot model, right? Try to change, as I told you last time, try to check those numbers so we can get more details. Here we use something new. In fact, last time we used the dropout, we used the dense layers. We did that plot model and the model summary. So the new here is using early stopping. I used here early stopping. And the early stopping is very important technique, and it will monitor the validation loss. You see here, it will monitor its early stopping. It's a technique which will stop learning process by monitoring the validation loss. And if this validation loss is increasing at some point, it will compare it with the training loss. And if it can see that there is a trend that the validation loss is started to increase, it should decrease, in fact. Validation loss, it should decrease with learning, but if it will start increasing, it will stop learning using this early stopping. And it's an approach we use to avoid also overfitting. So we try during the training process, we will monitor the validation loss. And if we can see that the validation loss started to increase, we will stop the training process. So after doing this, you can see here number of parameters here, it's 10 million. It's around 11 million weights, right? So now you have 11 million weights, and all your data points is 25,000 for training, correct? 25,000 for training, which is very little. So chances to overfit here, I mean, the data set is very, very small compared to the model size. So chances to overfit is extremely high. And therefore, we need to use dropout, we need to use maybe early stopping, for example. If you want to use early stopping, you must use a validation set. If you want to use early stopping, you need to use validation set because you need to calculate validation loss. Without validation loss, you will not be able to use early stopping. If you need to calculate validation loss, so we need to use a validation set. So here in this example, we will split the training data. We have 25,000. So 25,000, we will split it again into maybe 20,000 for training and 5,000 for validation. So we will use that part for validation. So as you can see here, X-train, it will be all data points from 0 to 20,000, and the rest will be used for validation. After doing this, we will fit the model. We will use the X-train, Y-train for training the model. We selected a box equal 25, batch size equal 512, and this is the validation. This is very, very important, the validation set. We need to have a validation set because I need to use early stopping, and early stopping should monitor validation error, correct, or validation loss. So we will use here the validation data. Without validation data, we will not be able to see to discover during the training process. Of course, you can train your model. I mean, without using this one, you will train your model for 20 epoch, which will take time. And after that, you will discover that your model is overfitted your data. So there is no way. I need to repeat this process one more time because my model will just memorize the training set, and it will not be able to generalize when we are testing it with the test set. So it's very, very important to maybe use early stopping all time because early stopping, it will save your time. So we will train the model, and after that, we will evaluate the model with the test set. When we are training the model, what happened? We want to train the model for 20 epoch. So we are starting at epoch number 1. And as you can see here, we have the training loss, which is very high. I need to use different color. So this is the validation. This is the training loss. As you can see, it's a high value in epoch number 1. And in epoch number 1, it decreases. It go down. With training, it will keep go down. And if you will keep training your model, this number will go down, correct? But in fact, it's not an indication. It's not good indication. The good indication is to look into this number and the blue number, right? We need to look into the red one and the blue one because the blue one, in fact, it's the validation loss. As you can see here, the validation loss also it's decreasing, but at some point it will, you see, it's going up. Now it will go up. If you will keep training your model, it will go up. So which means that your model will work very well for the test set. The performance will be very good for the test set, but it will be very bad for the training set. This one for the training. This one will be for the test. So the performance will be very good for the training, but it will not be good for testing because the model overfits. We need to discover this early. I don't need to wait until we overtrain the model for 20 epoch because the situation will be much worse. So now we are using the early stopping. Early stopping, will try to look into the validation loss, and when it sees that the validation loss started to increase, it will stop the learning process. So we will stop learning process at epoch number 4, and the performance here will be much better. So now we finished the training process here at epoch number 4, and we will test the model with a test set. When we are testing it with a test set, we got accuracy of 87%. If you will wait until reach epoch maybe 25, maybe this one will be much bad. Maybe it will be like maybe 20% or something, or 35%, 25%. So it will be very bad, because the model will be overtrained. When the model is overtrained, it will not be able to generalize, because it will just memorize the training data, and it will not be able to correctly classify the test set. So it's important to stop the training process at some point. So using early stopping, you will be able to do this. So this is a nice data set for sentiment analysis. Another classification also, it's sentiment analysis, but it's multi-class classification, not binary sentiment analysis, positive, negative, but it's multi-class classification. It's Reuters data set. And in this Reuters data set, it's short new wires. And their topics were published by Reuters in 1986. So it's very old, in fact, and it is used for text classification. Right? So you have number of topics. You have 46 topics, where some topics are more represented than others. Maybe those topics are maybe politics, maybe discovery, any topics, wars, correct, economy, and so on. And you have those news wires, and you need to classify it automatically. If you will get those news wires, you need to classify it. Is it politics? Is it maybe economy? Is it this and that? So each topic has at least 10 examples in the training set. And the data set consists of 8,982 training examples and 2,246 test examples. So the data set is already divided into one batch for training and one batch for testing. This is example from the training set XTrain 0. So this is a text, in fact, and it's the same way. You will have a dictionary, and so this is the input. Maybe to the model, this one will be my input, which is a sequence of words, sequential input. It's text, and this one the output. We agreed that there will be 46 topics. Sorry. Okay. So we will have we have 46 topics, right? We have 46 topics. So this vector, in fact, it will be 46 zeros, except one at the topic, the exact topic of this text, for example. So this input text, in fact, it's 0123 012. It's index number 3, correct? So this one will be classified into labeled as topic number 3. We need to see what is topic number 3 is. So it's the same way. We will use a dictionary because we need to limit it, and maybe we will look into the whole data set, and we will use a dictionary maybe of 10,000 or 1,000 most common used words, most frequent used, and we will find the index of the words which exist in the dictionary. We will put the index here, so it will be we will get vector of integers. Each integer here represents a word which is most common, correct? And we will skip the rest. We will skip the non-common words, right? We will keep only the most common words, because maybe those most common words, it will be indicative of the topic. So it can be used to classify each news wire into the right topic. If you want to load the data also, it's Reuters .load data. You need to define also the dictionary size, maybe 10,000, right? And in this case, it's a news wire will be encoded into a vector of size 10,000, right? It will be sparsely vector. So this is the word index. And so you will do this. you vectorize also. So each news wire will be represented as a vector of size 10,000. You will do it for the X-train and the X-test. You will convert Y-train and Y-test into categorical variables into one-hot encoding. So because this one now it's like this one. So Y-train will be like maybe topic 0, topic 1, topic 4, topic 10, topic 46, topic 41, topic 35, like this one all time. So we can just use one-hot encoding to convert this one into a large vector. The size of this vector will be 46 values. It will be zeros everywhere except at the index of this topic. It will be like this one, which might not be the most efficient way for doing it. So now we will try to build a model to classify it into one of those 46 topics. We will use also sequential ABI. We will use a hidden layer. Maybe this is the first hidden layer, will consist of 128 units. Activation will be ReLU. We will use this regularization techniques, L1 and L2. In fact, it's very, very important also for overfitting. So also we'll try to penalize the model for the values of change for delta omega. So the input shape in this layer will be 10,000 because this is the size of the vector, input vector. We will use also drop out with large values. We know it. We will use also, this is another second layer, drop out. And finally, we will have the softmax layer, which is the output layer. This one will be the output layer. Combine, right? Combine. Categorical cross entropy, not binary cross entropy, it's categorical because we have multi-class classification. We will train the model using X-train, Y-train. As you can see here, validation split will be 0.2. I mean, last time, in fact, we selected a set of images for validation. We have X validation, Y validation. So I can just, the validation data will be this one. But in fact, you can ask the model to, you can just define the validation split ratio 0.2, which means we will split X-train, Y-train by in random into 0.8 for training and 0.2, 20% for validation, right? It will be done automatically. So if you don't want to do it like last time, you can just here, specify the validation split. For example, 0.2. You will use also model summary and the model summary and the block model. And we will train the model using X-train, Y-train. We will train the model for 20 epochs. Remember here, we didn't use early stopping. Which means the model will be trained for 20 epoch. We have validation split, but we will not monitor the validation loss because we didn't use early stopping. We will be able to plot those curves, right, for the training and the validation, but we didn't use here early stopping. So we are expecting that this model will be trained for 20 epoch. As you can see here, training process starts from 1 and it will end at 20. And then when you look into the training loss will go down all time because the model will be trained. If you will train the model forever, this number will go down until it's flat. Correct? This one, it's the validation loss. The training loss, sorry. Validation, training accuracy also, it will keep increasing all time. So the most important is to look into the validation loss and the training loss at the same time to see if there is intentions for the validation loss to increase. Because if it will start increasing, it means the model will overfit, right? So the performance here, we need to check the performance here. So maybe this performance here would be like this one. So this is the accuracy of the training validation. And for the test set will be maybe 76.7% accuracy. Maybe if you can stop the training process at some point here, it might be better, right? It might be. We have 46 topics. So in fact, this one is a confusion matrix. And as you can see here, most of the numbers are located here, right? As the diagonal. But this one is not very clear. Maybe we need to use different approach for displaying the confusion matrix. So now, in fact, the last part, it's just building feed-forward neural network in Keras. So now we need to talk about convolutional neural network, CNN models. We need to use CNN models because CNN models are very smart, we don't need to worry about feature extraction if we will use CNN, because we just need to feed CNN with raw data, and it will automatically extract features from the raw data. So the goal of CNN is to learn higher order features in the data using convolutions. Convolutional layer is responsible for systematic applications of one or more filters to the input. So the convolutional layers, it will apply some kernels or some filters to the input image. And using convolution, we will try to extract feature maps. We will try to extract feature maps. The architecture consists of 3 types of layers. Input layers, we know this input layers, it will just accept the 3D input image, such as RGB, for example, video, sequential data, any numbers, and it will feed it to the next layer, which is the feature extraction layer. The second part will be feature extraction layers. It will be a number of CNN models, or a sequence of, or repeated sequence of convolutional and pooling layers. So we have an input layer. It will be followed by feature extraction layers. The feature extraction part, it will be repeated sequence of convolutional and pooling layers. And at the end, we will have classification layer or fully connected layers. So as you can see here, this is the input image. We will have some convolutional layers. Those convolutional layers, it will apply a kernel, pool, or a filter to the input image. And through convolution, it will generate feature maps. It will generate those feature maps, and it will, using convolutional and the pooling layers, it will create those feature maps, and it will send those feature maps to the second layer, and so on. So we will use usually the feature extraction part consists of maybe a number of CNN models, CNN layers followed by pooling layers. So the structure will be like this one. Maybe 1 or 2 convolutional layers followed by pooling layers, and we need to repeat this block maybe several times. So we can just repeat this one maybe 2-3 times. So we'll have convolution followed by pooling. After that, we have convolutional followed by pooling. As you can see here, it's repeated here, right? So it's the same. So it's CNN followed by pooling layer, followed by the same. Also, we need to repeat this one more time. So it will be another CNN model plus pooling layer. And at the end, we will get this high-level feature maps. And at the end, we will get those feature maps. We need to flatten it, which means we need to convert it into 1D vector. And we will feed it to the fully connected layer, which is like one hidden layer. This one will be the classifier. This one will be the classifier. So we will get those feature maps, convert it into 1D vector, and just send it to the classifier. And the classifier, it will classify. The classifier consists of maybe one hidden layer and one output layer, for example, as you can see here in this example. Maybe in this dense layer, we will use ReLU. And in this one, because it's multi-class classification, we will use softmax activation function. So I mean this is in fact this is deep learning, so it's simple. So it consists of this feature. I mean this is the input data, which is RGB image, for example. We have this feature extraction part, and this feature extraction part, it will try to extract a feature map, and we will send this feature map to the classification part. And the classification part, it will consist of maybe one hidden layer, one output layer, or more hidden layers. So it's according to your application and according to your choice. Sometimes they call it softmax classifier because in the output layer they use softmax activation function because we need to calculate probability. Softmax activation function, it will calculate probability, right? So the building blocks of the convolutional neural network, we have 3 types of layers again: convolutional layers, pooling layers, and fully connected layers. So now it's easy. Also, we will use sequential API. If you want to build it in Keras, you need to use sequential API. So the convolutional layers consist of filters and feature maps. In fact, filters, we need to number of filters. We need to select the size and number of filters, and each filter will generate a feature map. So if you selected 10 filters, what will happen? We will obtain 10 feature maps as an output from this convolutional layer. So hyperparameters here will be number of filters and the size of each filter. Filters are essentially the neurons of the layer. I mean, each filter, in fact, it is a neuron, correct? So I will explain it here. Maybe I will select a feature which is 3 times 3, correct? It would be like this one. So in fact, each filter here or each pixel value here consists of weight value omega 1, omega 2, omega 3 until omega 9. So in fact, each filter here can be represented by a neuron. If my convolutional layer consists of 10 filters, so in this case, I will have 10 neurons from 1, 2 until 10. And each filter, each neuron will be connected with this filter. So how many inputs? The inputs, because in convolutional, in fact, we apply this filter to the image and move it from left to right and from top to bottom by 1 pixel. So, and we will apply it one by one like this one. So in fact, how many inputs to each neuron here? It will be 9 inputs. So it will be like this one. 1, 2, 3, 4 until 9. So this one will be connected to this one. Correct? And also this one will be connected to the second one. So it will be like this one. So number of inputs here will be, I can call it x1 to x9. So it will be like x1, x2 until x9. And we will have different weights, right? So in this case, if you have 10 filters and the filter size is 3 times 3, how many weights we will have from this layer? How many weights? And of course, when you apply this filter to the image, it will generate 1 pixel value. So the output feature map here, each one here will generate a feature map. Each one here will generate a feature map. When we apply it, if the input image is like this one, we will apply it in that part, and we will create this input first pixel. Correct? We will get this one. We will move the filter. Maybe we will move the filter to that location here, for example. When we move it to that location here, it will generate this pixel value. Correct? And so on. So how many parameters here of this layer, for example, if we are using 10 filters and each filter is 3 times 3, number of parameters will be 10 times 9, correct? Plus, of course, remember the bias, because each one of those has 1 bias, and we have 10 of it, so we should have 10 bias. So in this case, number of parameters here will be 100. Another way for calculating it, you can just say it's number of units, number of feature maps, multiplied by the feature by the number of filters times the filter size, which is 3 times 3 plus 10. So it will be 90 plus 10 also, it will be 100. So we will get the same number. So filters are essentially neurons of the layer. They have both weighted inputs. Those are the weighted inputs, omega 1, 1, omega 1, 2, and so on. So this is weighted values. And generate an output like a neuron. The input size is a fixed square, and the input size is a fixed square. We need to decide the size. It could be 3 times 3, it could be 5 times 5, 9 times 9, 11 times 11. Correct? So the input size is a fixed square called a batch or a receptive field. Each filter has a receptive field. And if the convolutional layer
Hi, can anyone hear me?
Yes, please.
It just, sorry. It looks like everything freezed in my side, but no, sorry.
Yeah. So sorry, just my internet sometimes. So the input size is a fixed square. We call it batch or receptive field. And if the convolutional layer is an input layer, then the input batch will be pixel values. I mean, when this CNN model, when this CNN layer is the input layer, correct? So now the input to this first CNN will be the raw data image. So it will be pixel values. But this layer will generate a feature map. It will not be a pixel value, but it will be just float numbers. And we can feed those numbers as the feature maps to the second layer. So only the first CNN will deal with pixel values. The next will not. So if they deeper in the network architecture, then the convolutional layer will take the input from a feature map from the previous layer. So feature maps is the output of one filter applied to the previous layer. A given filter is drawn across the entire previous layer, moved one pixel at a time. Each position or each application will result in an activation. So because if you have this image like this one, I will apply the filter here, correct? So in fact, we will do multiplication. I will just do convolution where we multiply those weight values by the related pixel values and get average, for example, or weighted sum. It will be like, do you remember omega x plus b? It will be like this one. So the output pixel value, it will be all time using this one, omega x plus b. But omega here, how many omegas? Omegas will be number of weights of this filter. If the filter is 3 times 3, so it will be omega I equal 129, right? And it will be applied to that part, which is the receptive field of this filter. And after this application, we will move it one step to the left, to the right. We are starting from left to right, and from top to bottom, right? So it will be like this one. We will move it by one pixel value, do another application or activation, and so on until we scan the whole image, until we finish the whole image. So if the receptive field is moved one pixel from activation to activation, then the field will overlap with the previous activation by field width -1. Usually, when we apply this filter, I apply it here one time, and we will move it by 1 pixel to the right. So it will move by 1 pixel to the right. It will be like this one. We will do another application. So as you can see here, there is overlap between each activation, which is the field size -1. Another application, we will move it another one, so it will move like this one. So it will be like this one. So we will do some activations each time, and we will update the weights based on those activation, of course, right? Until we scan the whole image. We will do this one until we scan the whole image, until we reach this point. So in fact, when we are working with deep learning, the size of the input image is not important because the size will impact only number of activation. So if you have a larger image, you will just need more activations. That is it. So the distance that the filter is moved across the input from the previous layer, each activation is referred as a stride. I mean, it will move by 1 pixel each time. We call it stride. So the distance that the filter is moved across the input from the previous layer, each activation, we call it stride. By default, stride equal 1. So we will move it 1 pixel at a time. We can use something called zero padding to invent this mock inputs with zero values from the receptive field, not to read off the edge of. I mean, sometimes here, when we do this application, in fact, the size of the output feature maps will be shrinked a little bit. It will be reduced. Why? Because we do this activation and we calculate maybe the pixel value in the middle. So we will lose one row, and we will lose here one row. We will lose from that side one column. We will lose here one like this one. So in fact, when you do this application, we are losing. In fact, we are losing some. I mean, the output feature map will shrink from all sides by 1 pixel. To avoid this, we can use something called zero padding. And in this zero padding, we try to have this mock. We try to invent this mock inputs. We try to add maybe zero bits or 0 pixels from around the perimeter. We will have this one, all zeros. We will adjust the zeros from here. And in this case, in fact, when we do this application, we will get the same size of the feature map, output feature map will have the same size as the input image when we are using zero padding. I have here some details, for example. So zero padding, when we apply in convolutional layers, we lose some pixels around the perimeter of the input image. It can add up for successive convolutional layers. So in this case, if you have, for example, 10 convolutional layers, and each time you don't use zero padding, so the output feature maps will shrink with time, over time. You will do it 10 times, for example. So in this case, you will lose 10 rows from top, 10 rows from bottom, 10 columns from left and right. So the output image or the output feature maps will shrink a lot. And maybe in this case, we will lose some information. To avoid this problem, you can use zero padding. So zero padding, when applying convolutional layers, we lose some pixels around the perimeter of the input image. It can add up for successive convolutional layers. One solution is to add pixels of zero values around the boundary of our image. So because imagine that I don't have here zero padding, so I will apply this kernel to that part, because this is my input image. When we apply it to that part, in fact, we will get a pixel value. Maybe I will have this pixel value. I will do it here like this one. Okay, I will get this pixel value here. I will move it by one. I will move it by one pixel to that place, and I will calculate this one. I will go down here, do this calculation. I will get this one. I will move it again to that location. So in this case, do you see we got only 4 pixels. So if you will not use zero padding here, the input image here was 3 times 3. I mean, this one was 3 times 3. So now the output feature map will be 2 times 2, correct? So it will shrink. If you want to avoid this, you need to use zero padding. So in this case, we will add rows and a column of zeros around the perimeter of the image, this one. Now we will apply it here. When we apply it here, we will get this one. It's weighted sum, so it is 0 times 0 plus 1 times 0, all times 0, it will be 0. We will move it by 1 pixel because stride by default equal 1. Apply it multiplication, so it will be 3 times 1. We will get 3. Move it here. I will move it to that location now. So it will be 1 times 2 times 6, it will be 8, correct? Move it here, so it will be 2 times 4, it will be 4. Go down by 1 pixel. So we will go down here by 1 pixel, starting from left to right. So it will be 3 times 3, it will be 9, and so on. So in this case, when you are using zero padding, the output feature map will not shrink. Pixel value describes how bright the pixel is and or what color it should be. I mean, of course, we have 3 layers, correct? RGB. So we'll get 3 numbers. In each pixel value will have 3 numbers. Each number will represent the color. If it's a grayscale, it will be maybe black and white. If it's RGB color, it will be just color. Stride by default, the filter strides 1 pixel at a time, sometimes either for computational efficiency or because we wish to downsample, we move our window more than 1 pixel at a time. If you are moving here 1 by 1, you will get this output. But if you will move it 2, what will happen? The output feature map will be shrinked because number of activations will be less. So we can do a kind of downsampling, right? So if I will apply it here, I will get this number. I will cover it here. And if you move by 2, I will get this number. So I will get another number here. We will go down here. So it will be downsampled, right? So the size will shrink and we use it for downsampling if you need to increase the stride. And when you use a stride not equal 1, it will enhance, in fact, the speed of, because number of activations will be less. Number of activations, it's number of calculations. So if you will increase stride from 1 to 2, in fact, you will reduce maybe number of calculations or activations by 50%. So your model will be much faster. But also stride, it's something which is it's hyperparameter, correct? So maybe someone, he will select one, another one. Maybe if you are working with large images and you need to do a kind of downsampling to enhance the efficiency, you can just use stride equal 2, 3, 4. and it's according also to the size of your kernel, correct? Because I cannot jump values. Maybe I can decrease the overlap, because maybe if I have 3 times 3, so it will be like this one. If we use a stride equal 1, so each time I will move by 1 pixel. But if you will use a stride equal 2, you will move by 2 pixels. So we will reduce the overlap between each activations, correct? So it will be like this one. So you need to get some overlap. This is very, very important. You cannot use stride equal 4, because now in this case I will take one activation here and the second activation will be like here. So now we are losing this information in the middle, correct? We don't count it. So we have something called the pooling layer, and this pooling layer, it's downsampling most techniques, so it has the same impact as stride. Downsample the previous layers, feature map. Pooling layers follow a sequence of one or more convolutional layers and are intended to consolidate the features learned and expressed in the previous layers. So this pooling layer is downsampling, right? So it's 2 times 2 max pooling. So just apply here this filter, 2 times 2 max pooling. Take the max. So the max between 0, 1, 3, and 4, it will be 4. Move it by 1. So when we move it by 1, it will be here. Take the max. Max will be 5. Go down. What will be the max? Max will be 7. Move it by 1. Max will be 8. So it will be this one will be the upper feature map from the max pooling. So it's downsampling, correct? And consolidating the features which are learned in the previous layer. So max pooling is very, very important. Usually, they use 1 CNN or 2 CNN followed by a pooling layer. And you need to repeat this block maybe several times. So they compress or generalize feature representations. We do compression here now, because now we will go down from 3 times 3 into 2 times 2. So in fact, we do compression, right? They compress or generalize feature representations and generally reduces the overfitting of the training data by the model. They have also a receptive field, often much smaller than the convolutional layer. Also, the stride or number of inputs that the receptive field is moved for each activation is often equal to the size of the receptive field. Usually, in this max pooling, it's not moving by 1, but it must move by the size of the receptive field. I mean, now it's 2 times 2, so stride here should equal 2, right? So we don't need to have overlapping when we do this kind of downsampling or max pooling or average pooling. We have max pooling. So max pooling, we will take the max. If it is average pooling, we will take the average. We will take weighted sum or average of the 4 values. So instead of max pooling, it will be 0 plus 1 plus 3 plus 4. So it will be 8 divided by 4. So instead of using 2, it will be 2. 4, it will be 2. This one, it will be 1 plus 2, 3. Plus 4, it will be 7. Plus 5, it will be 12. Divided by 4, it will be 3, for example, if it's average pooling, and so on. Pooling layers are often very simple, taking the average or the maximum of the input value in order to create its own feature map, right? So very simple approach. It does not have any parameters. So when we have this max pooling layer, we should not expect that it has any parameters. It's just calculation process. At the end, we will have this fully connected layers, and this fully connected layers are the normal. It's flat feed-forward neural network. We know it. So here in this model, we are starting with the input volume. We will have some convolutional layers, followed by max pooling layers, correct, and so on. And at the end, we will have a feature map. We need to flatten, before sending those feature maps to the fully connected layer, we need to flatten it. And flatten it, it's also a layer, in fact, called the flattened layer. And this flattened layer does not have any parameters. It will just convert or combine all those feature maps into 1D vector. We have here a number of feature maps. So we just need to combine all those feature maps into 1D vector. It will be like this one large 1D vector, where we will feed all those numbers to the fully connected layers. So it will be, we will feed those numbers to each one of, correct? So it will be like this one. It will be like this one. So finally, we will have the fully connected layers, and the fully connected layers are dense layers. May have a linear, nonlinear activation function or softmax activation function in order to output probabilities of class prediction. Usually, in those hidden layers, we use ReLU, for example, and in the output layer, we need to use softmax. Softmax layer, we use it to calculate probability. Connected are used to the end of the network after feature extraction and the consolidation has been performed by the convolutional and the pooling layers. They are used to create final nonlinear combination of features and for making predictions by the network. So this is the most important. We know this part very well, correct? This is traditional machine learning part. What is new here, in fact, is the feature extraction part. We just added the feature extraction part because we need to extract features and feed it to the classifier part. In Keras, it provides implementations of the convolutional layers called the conv2D, and it requires the expected shape of the input images in terms of row, column, and channel. I mean, we need just to define. I mean, we will use this. In Keras, we have a layer called the conv2D. We need to use conv2D if you want to use convolutional layer. We need to use conv2D, and this conv2D, it's expecting from us to get the shape of the input image. So when we are feeding it with an input image, we need to provide the shape of the input image. And the shape will be in terms of height, width, and depth. So we need to provide this number. Dimensions. And also we need to provide the number of filters. And those filters will contain weights that must be learned during the learning process. And the filter weights represent the structure of the feature that the filter will detect. And the strength of the activation indicates the degree to which the feature was detected. I mean, you have the filter, and the filter will contain number of weights. And of course, maybe those numbers, some numbers will be positive, some numbers will be negative, correct? When it's large number, for example, the absolute value is high, it indicates that maybe this pixel value is important, right? The layer also requires that both number of filters be specified and the shape of the filter be specified. So we need to define number of filters and the size of filter size. So it's a hyperparameter. You need to select the number of filters and you need to select filter size. If we need to implement it in Keras, we have this nice structure. First, you need to maybe import sequential and the model APIs from Keras.models. We use the sequential, we use the model. We use sequential for building sequential models, model of sequence of layers. Model, we use it if we need to customize a model to get access to some specific layers, right? We need to block outputs from some layers. So in this case, we need to build this, we need to use model API. From layers, we need to import dense, conv2D, for example, and the max pooling 2D. I mean, those are the layers which will be used to construct our deep learning model. After importing those standard libraries, we need to build our model. So as we know, we need to use sequential API. We will just add those layers. We add dense layers. This one will be the classifier. But before this one, we need to maybe to add conv2D and the max pooling to build a deep learning model. We need to configure your model using compile. You need to define the loss. For example, the optimizer which you want to use, the metrics. And after that, you need to train your model using X-train, Y-train. You need to specify number of epochs, maybe the batch size, right? You need to evaluate your model on the test set, correct? And you will get this loss and the metrics, for example. And after that, you will use your model for maybe testing. I mean, if you want to plot the maybe if you want to plot maybe confusion matrix, so you need to get the predicted classes and you need to plot it against the actual classes, correct? So you need to use predict. So in fact, it consists of maybe this train, correct? Maybe train, predict, train, evaluate, and predict structure or something. So first we need to build the model, configure your model, train your model, evaluate, and predict your model. It's very similar to the structure which we saw in pipelining, right? If you want to understand the meaning of those convolutional filters, or convolutional layers, how they work, we can talk about some edge detection filters, which we use in classical image processing techniques. So maybe you have an image like this one, for example, and you need to detect those vertical edges and horizontal edges, right? So those vertical, I need to predict those vertical edges, correct? You see, maybe those are the vertical edges. All those, those things, those are vertical edges. I need to predict those vertical edges. And at the same time also, I need to use another filter for predicting those horizontal edges. This one will be horizontal edges. So as you can see here in this image, it's not very clear, but you can see here those vertical edges, we can detect it. In this one, we can predict those vertical edges. All those vertical edges we can predict, right? We can predict those. So in fact, those horizontal edges and vertical edges, we can combine it again and try to calculate number of maybe edge detection, for example, and calculate number of pixel values of the edges and use it as an input feature to my machine learning model. If we want to use classical image processing techniques. So the idea here is that you have a filter and you apply this filter to the image, and the output from the feature will be this feature map, right? Maybe it's vertical edges or horizontal edges. Maybe those vertical edges will be one feature, this one will be another feature. So how this vertical edge detection work? You imagine that we have an image like this one. As I told you, zero values are maybe black pixels. So black pixels will be represented by zeros, and white pixels will be represented by non-zero values, which is large values. So we have this image, it's 6 times 6, and I will use this 3 times 3 vertical edge detection. This is a filter or a kernel, and this kernel consists of weights or numbers. 1, 1, 1, 0, 0, 0, 1, 1, 1. So in fact, if you can compare this one with a filter of TNN model, it will be the same. So we will have the model filter like this one, but instead of using those numbers, we will have here weights, omega 1, omega 2, omega 3, until omega 9. And during the training process, we hope that we initialize those weights. Before the training process, we initialize it with small random values. And after the training process, we will get some numbers here. We will get some numbers. Maybe this one will be 0.6, maybe this one 0.7, maybe 1, 0, 0, maybe 0, 0.8, 0.9. Maybe it will be something like edge detection. But we are not expecting to get exact values because the model here will have more freedom, in fact, to invent new filters. So this one, it's a vertical edge detection. But in fact, in my model, in my first conv layer, I just decided to use maybe 10 filters. So we should expect that we will get 10 different filters. And each filter will try to detect something different. Maybe from those 10 filters, we will have a filter which will try to detect vertical edges. Maybe we will have another filter which will try to detect horizontal edges. Maybe, and many other filters. So all those filters will try to detect something which makes sense to my classification problem. So when you apply this one to this image, so I will just do convolutional here. I will apply it to that part. Calculation, do the calculation. So it will be 1 times 10 minus, so it will be 0. We will get 0. And 0 is what? 0 is white pixel. 0, sorry, is black pixel. So we will get this black pixel here. We will move it by one pixel. We will do this activation. We will do the calculation. We got 30, which is white pixel. So we got here a white pixel. We will repeat this process. We got another white pixel. We will do it one more time. We got black pixel. So as you can see here, the first row, in fact, in this image, it's like this one. One black, one white, white, and black. And as you can see, this is my image. In fact, we try to detect the vertical edge. I have here a vertical edge because it's the boundaries between white and black. So I have here an edge. So I need to detect it. So here I will get here black, which means there is no edge. There is no edge. But here in the middle, we found that there is an edge. So in this edge, we will put it by white. So we will replace this edge with a white line. We will repeat this process, just repeat it, and so on. So at the end, we will get this one. From this image, this one is the input image, and we will convolve it against this filter, and we will get this one as the output feature map. So now we will be able to detect those vertical edges, right? Because at each vertical edge, we will have white line. So if you can go here to this figure back, no, it will take time. So there are many edges. So is this one for vertical edges? If you can transpose it, so transpose and apply it to the same image, you will get horizontal edges. There are many other edges also. Maybe this horizontal change, this is vertical change. So there are many filters. In fact, if you can open any classical image processing textbook, you will find many filters. So, but the idea here, we have here 4 filters. So you can apply those 4 filters to the input image and try to extract features by yourself. It's a very, very time-consuming process and very tedious. In feature extraction part, we try to automate this process using convolutional layers, right? So the convolutional layer, we just need to define how many filters you want to get. You can just say, I need to get 32 filters. Can you imagine what will be the filter size? It will be 3 times 3, correct? What will be the input shape? Input shape will be this, and they train your model. So you should expect that the first layer, it will invent 32 filters, different filters. Can you imagine? 1, 2, 3 until 32. And each one of those filters will generate something different. Maybe one of those will be vertical edges. Maybe one of those will be horizontal edges. Maybe this one will be something else, and so on. So number of feature maps which will be generated from this layer, it will be 32 feature maps, because each filter will generate a different feature map. So we will get 32 feature maps. We will feed those filters, feature maps, to the second layer. The second layer, it will repeat the same. It will try to invent a new filters, which will try to combine and try to find something else which makes sense. We repeat this process, and during the learning process, we hope that we will be able to converge to something which makes sense at the end. So when we have the feature maps at the end, before flattening layer, we hope that we will get something which will make sense for our classification problem. So in this case, you just need to feed your CNN model with your raw data. You don't need to use anything else, just raw data. We talk about padding layer. It's a zero padding. We mentioned it already. Zero padding, to overcome these issues, we can pad the image with an additional border. We add 1 pixel all around the edges, just zero padding. So in this case, the output shape will not shrink. It will stay as it is. Stride, we talk about stride and stride convolution. I mean, this stride, we just move by 1 pixel. For padding, in fact, I want to say something also about padding. If you have an image like this one, and we will not use zero padding, what will happen? We will scan that part 1 time. We will move it by stride equal 1, repeat this process, go down here. As you can see here, I mean, the next part here, that part is scanned only 1 time. That part, this pixel scanned 2 times. This one scanned maybe 3 times. So in fact, what is going on here is that if we will not use zero padding, we'll try to tell the model a message that information which is inside the image is more important compared to the information which are close to the borders of the image. I mean, the information which are coming from those corners are less important than anything else, in fact, because these pixels will be scanned only 1 time. There is no overlap here. So these pixels will be scanned only 1 time. And also, those pixels will be scanned much, much less compared to the inner pixels. And this, in fact, gives a message, a hidden message to the CNN layer that please focus on the information in the middle. Forget about information which are coming from the outside, from the borders, from the perimeter. So we will focus on the information which are coming from the middle. And this is a problem because if you have, for example, an application where I have an autonomous car, and my autonomous car here, it has camera here, correct? And we are taking images of the road, and we try to analyze it so we can avoid hitting people, stuff like this. If you have someone is crossing in a zebra cross, or someone crossing the road, for example, he is crossing it from this side, for example. This information, just I told you here, that the model knows that this information is not very important. The information from the middle is more important. So if you have a car coming in front of you, you will try to avoid it, because this is more important than the information which are coming from the sides, top or bottom or something. So if someone is crossing, maybe you will not stop for him, but you will stop for a car which are coming from the middle, because you send a secret message or a hidden message to your model that the information which are in the middle are more important compared to the information which are coming from the sides. Stride is one, we will not talk about it anymore. It's the downsampling and the consolidation of the feature maps learned, and it will help also to reduce the size of the image. I mean, because we do downsampling, so we are expecting that the output feature maps will be downsampled. It will be, in fact, we will reduce the size by maybe by 75%. And when we do this, it will reduce number of iterations in the next layers. So in fact, when we use Stride, it will help us to downsample, consolidate feature maps, features learned, and also it will increase the efficiency of my model. It will be faster. This one, it's convolution of size 2. If we need to do Stride with size 2, for example, we will do one. Here we will do one convolution. We will get this number. We will move by 2. We will get this one. Do you see what happened? We will move by 2. We got this one. Go back by 2. Right? We go here by 2. We do convolution. We got this one. Another 2. We got this one. Another 2. We got this one. We go by 2 again. 2 pixels down. We do this for last. So do you see what happened? When we use a Stride also of size equal more than 1, for example, it will have this kind of downsampling also effect. So, and as you can see here, we just did 9 calculations. We did 9 calculations or 9 activations, and we reduced the image size. It goes down from this size to this size when we increase the Stride. So also it will have this downsampling impact. In fact, it's a good effect, because it will help us also to generalize. It will help the model to generalize. So we don't stick to those small details in the input feature maps, but we will try to consolidate feature maps and try to create more abstract levels of the representations of the feature maps. And we have been working with this. I mean, what will happen if you have volumes, if you need to do convolutions over volume? Because in the first layer, for example, maybe the input image will be RGB, or maybe it's a grayscale image. So the filter will be just 3 times 3, one layer, 2D, for example. We will apply it, but in fact, the feature maps generated from this conv layer. If you selected, for example, 10 filters, so 10 filters will generate 10 feature maps. So we will have like one image of 10 channels. So for the next layer, when we select the feature, when we select the filter size of 3 times 3, those 3 times 3, it should be applied to the whole volume. So if you have 10, so this one will be automatically modified into 3 times 3 times 10 to be able to apply it to the whole input volume, right? So we can talk about it like working with RGB image, because it's much easier if the input is RGB image. So in this case, if you will select the filter as 3 times 3, it will be automatically converted into 3 times 3 times 3. Why 3 channels? Because the filter should have number of channels equal to the number of channels of the input volume. So if the input volume has 3 channels, your also filter will be 3 channels, and you will apply this part here. When we try to convolve, so it will be applied part here. Yes, another part here inside. So, and we will apply it one time, and we will get only one single value. So in this case, number of parameters will be 3 times 3 times 3, which is 27, not 9. we will one application we will get this value, another application because we agreed that each filter will generate only one feature map. So the output from this filter, it will be this one channel. So this is how if you have two filters, what will happen? So I have two filters, 3 times 3, and the input volume is has 3 channels, for example. So this one automatically will be added, will be adjusted to have 3 channels. If I have two filters, this one will generate one feature map. This one will generate another feature map. So the output from this layer will be 2 feature maps or 2 channels. You can just say it's 2 channels. We have something called one layer of convolutional network. One layer, only one layer of convolutional network. Once we got an output after, this is just explanation how it works. I explained it already. So just need to calculate omega x plus b. So when you have a filter, so if you have maybe first conv layer consists of maybe 10 filters. So in fact, each filter will be just a perceptron. Number of inputs will be the size of your kernel or feature maps. And you just need to calculate this function. We need to calculate net. I will call it net equal omega x plus p. And after that, we need to apply this one to the activation function if it is RELU, for example. So we need to get f net, which will be this max between 0 and the net will be like this one, correct? So that is it. So it's simple. Pooling layers, we'll talk about it. It's for downsampling. Just sorry for this repetition. So we will do this. It's usually 2 times 2, and it moves with stride equal to the size of the kernel. So if the kernel is 2 times 2, we will move by 2. So we will apply it here. We will get the maximum, which will be 9. Move by 2, get the maximum, which will be 2. Go down by 2, get the maximum, which is 6. Move by 2, get the maximum, which is 3. And that is it. So we do this kind of down sampling. We have CNN example here, which is AlexNet. AlexNet, it consists of 60 million parameters, 60 million, but no problem, because today, in fact, we build a model which consists of 10 million. Do you remember it? Or around 11 million. So we build a model for text, for sentiment analysis, and the model consists of 10 million. It was not deep learning. It was just a very normal, straightforward neural network, but the size was very large. So this one consists of 60 million. And it uses RELU activation function. And as you can see here, this is the input volume. It's RGB image. This is the height. This is the width. This is the number of channels because it's RGB image. It consists of number of CNN layers followed by max pooling layer. So this block is CNN and max pooling. This one will be CNN and max pooling. This one will be CNN, 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 and the max pooling. You see? So now we have this block. This one 3 CNN plus max pooling. So anyway, this is the input image. We will apply, we have the first conv layer. The first conv layer has defined 96 filters. Each filter has a size of 11 times 11 with a stride equal 4. You will apply this one to this function. You will get the size will shrink because we didn't use zero padding. So the size will shrink from 227 times 227 to 55 times 55 times 96. 96 because we have 96 filters. Do max pooling. Max pooling will reduce the size by 75%, as you can see here. Max pooling, it will make it like this one. So if this is the input image to the max pooling, the output size will be this one. So in fact, we reduce 75% of the size, correct? Now the size is special dimension are less, 27 times 27, so it's not smart to use 11 times 11. We reduce the filter size to 5 times 5. Same, it means here we use zero padding. When you use zero padding, it means the output size, special dimension will be the same, 27 times 27. But number of features here was 96. Here we defined 256 features. So number of channels here will be 27 times 27 times 256. Apply max pooling. When you apply also max pooling, it will go down to 13 times 13. We're reducing it further to this one. Apply max conv layer by 3 times 3, same 3 times 3, another 3 times 3, correct? Right? So we will get at the end 256 feature maps, and each feature map has a size of 13 times 13. Apply max pooling. When it's 13 times 13, just divide it by half. So it will be 6 times 6, correct? So this one will be 6 times 6. It will be that part. So at the end, we will have 256 feature maps. Each has a size of 6 times 6. And it's a very large volume, as you can see here. Before applying it to the dense layer or the fully connected layer, we need to flatten it. So we need to have here a flattened layer. And this flattened layer, it will combine those feature maps and convert them into 1D vector. The size of this vector will be this number. And this number, in fact, it's 6 times 6 times 256. So this is the input to the next layer. So the fully connected layer will have a size, number of units will be 4096. The second one will be the same. And finally, we will have a softmax layer, which consists of 1000 outputs. Because in this AlexNet, in fact, we try to classify objects into one of those 10,000 objects. What is the best practices when we are using convolutional neural network? I mean, input receptive field, I mean, dimensions, the default is 2D for 2D images. It could be also, it's 3D also for RGB images and videos. It could be also 1D for words or a sentence. So I can use a filter which is 1D, not 2D, correct? So it could be something like this one, correct? 1D for words, because the word is a sentence, sequence of words. And as you mentioned, I mean, as we discussed last time, we convert it into very large, for IMDb, it was very, very large vector, which consists of 10,000 values, right? So in fact, you can convert this one into image and apply so you can just reshape this one into an image and apply 2D filter. So you can just keep it as it is. And in this case, apply 1D filter to this one. Batch should be as small as possible, but large enough to see the features in the input data. It's common to use it. Usually people use receptive field 3 times 3 on small images, and 5 times 5 or 7 times 7, and more on large images. So here in AlexNet, because it's 227 times 227, they used 11. Receptive field is 11 times 11. Because it will help the model to see more, in fact, right? Stride default equal 1. It's easy to understand, and you don't need to padding to handle the receptive field falling off the edge. So anyway, you can use 2 or large for large images if you need to speed up if you want to make your calculations more efficient. Number of filters. Filters are the feature detectors. Generally, fewer filters are used in the input layer, and is increasingly more filters used in the debug layer. And it's the same here. We are starting with 96 filters. 96. Now, when we are going deeper, we increase the number of feature maps. 96, 96, 200. It's detectors. 256, 256, 384, 384, 256. Right. So we are starting usually with less number of filters and increase this number when we go deeper in our model. Padding, set it to 0 and call 0 padding when reading non-input data. When you are working with non-input data, we don't need to use it. Right? This is useful when you cannot or don't want to standardize input image size, or when you want to use the receptive field. And so anyway, usually we use this padding when we are working with input images. Maybe in the feature maps, maybe, I mean, there is no need to use it, because the most important is to focus on the information coming here from those sides, right? So it's very, very important to use 0 padding when you are working with input data, raw data. Pooling is destructive or generalization process to reduce overfitting. Receptive field size is almost 2 times 2, with a stride of 2 to discard 75% of the activations from the output of the break. Usually it will be like this one, standard. Data break preparation, consider standardizing input data, both the dimension of the images and the pixel values. The pattern architecture, it is common to pattern the layers in your network. This might be 1 or 2, followed by pooling layer. Usually it will be like this one. And it can then be repeated 1 or more times. So you can say that feature extraction part, it will consist of number of blocks. Each block will be 1 conv or 2 conv, followed by pooling, and repeat this block maybe 2, 3 times, and that is it. Dropout, CNN have a habit of overfitting, so even with pooling layers, a dropout should be used, such as between fully connected layers and perhaps after pooling layers. Also, dropout is very important, so we can try to limit the model capacity in a way to avoid overfitting. There are some data sets I wish if you can play with it, like CIFAR10, for example. CIFAR10, it's a data set which consists of 60,000 images. Each image is 32 times 32, and it consists of 10 classes. The data set includes 6,000 image per class because we have 10 classes. So 10 times 6,000, it will be 60,000. The data is divided into 50,000 for training and 10,000 for testing. The data set is divided into 5 training batches and 1 batch for testing, each with 10,000 images. So the batch size here is fixed. The test batch contains exactly 1,000 randomly selected images from each class because we have 10 classes. So 10 times 1,000, it will be 10,000. And the size of the test batch is 10,000. The training batches contains the remaining images in random order. If you want to get it, you can import it from Keras datasets. It's called CIFAR10. There is also a version of CIFAR10 called CIFAR100. And this CIFAR100, it's much extended. In fact, it contains those sober classes and the classes, number of classes, and under each class, maybe we have 5 classes. So for each sober class, we have 5. I guess we have 20 sober classes grouped into 20 super classes. 1, 2, 3, 4. Yes, maybe it's 20 super class, and under each class we have 5 classes. So it will be 5 times 20, it will be 100, right? So we have 100 classes. It's also, if you want to use it, it's from Keras.datasets. You need to import CIFAR10. Another also data color facial recognition. It's 8.5 gigabytes for facial recognition, and it consists of this number of images, 14,000, and 1,199 persons. And there are 365 duplicates. You can use it also for building classifications or classifiers. This is CIFAR10. Import it from Keras.datasets. It's already classified. When you're importing it, it's already divided into X-train, Y-train, X-test, Y-test. You can block it, and you can build a model for classifying CIFAR10. It will be the same model as we used before, but the difference here will be just in the configuration. So the input shape will be 32 times 32 times 3, because it's RGB images. Height is 32 pixel values, and width is 32 pixel values. We need to select here 32 filters, followed by dropout, another conv layer, followed by the max pooling. So as you can see here, we have 2 CNN layers followed by max pooling. After that, we will get the output feature maps here. We will flatten it. And after we flatten it, we will send it to the first fully connected layer, which will be a dense layer, consists of 512 ReLU, followed by dropout. And after that, we will have the output layer, which is softmax layer. As you can see here, number of classes will be 10. Compile, model summary, plot model, you will get all those numbers. If you want to check this number, how can we get this number? We need to look into number of filters. If you need to this one, so we need to look into how many filters we have. We have 32 filters, right? 32 filters. What will be the filter size? It will be 3 times 3 times the number of channel of the input. The input will be 32 times 32 times 3. So we need to multiply again by 3 and add 32 bias. You will get this number. Dropout does not have any parameters. Another conv layer. Max pooling does not have any parameters. Flatten does not have any parameters. dense layer, this number, if you want to get this number, it will be this number multiplied by this number plus this number. So this one will be 512 multiplied by 8192 plus 512. You will get this number. Drop out has no parameters. Dense layer, this number, it will be 10 times this plus 10. You will get this one. So this is the total number of parameters here. It will be 4 million, more than 4 million parameters. You will train the model. You need to fit the model. It's important to use early stopping here, but we will train the model here for 20 epoch. We didn't use early stopping. So you can see the training loss and the validation loss. So we trained the model for 20. I need to check those numbers, in fact, because we should not get number more than 1. So I need to check. This is the accuracy for training and loss. As I told you, if you want to plot some intermediate values, so instead of using, I mean here, when we are building our model, we use the sequential API for building our own model. But if you want to get access to some specific layers, we need to use model API. So here we will use model API. Model API has 2 inputs, two arguments. The first one will be the inputs, and the second will be outputs. Inputs will be model.input. Outputs will be model.layer, specify the layer number or name dot output. So now here we try to get access to the output from layer 2. So layer 2 will be, I guess it's this is input layer, maybe 0, 1. Maybe it's a 0, 1, 2. Maybe we will get this output from here, right? After this drop out, or after conv2d, for example, we will get this output here, which will be 32 times 32 times 32. We will do plotting as we did last time. This one was the input image X-test. I will feed this model. We call it base model, right? I will feed this base model with an image, which is X-test1, for example. And the output will be the output from the base model. Yes, so feature map, it will be feature maps. So this is my base model dot predict image, which is X-test1, and we will get the feature maps. Those feature maps will be what? It will be 32 times 32 times 32. So in fact, it will be 32 images or 32 feature maps of size 32 times 32. Plotting it, it will be like this one. So this is the input, and this one will be the feature maps, which we are getting from maybe the first conv layer, right? As you can see it here, we will get those feature maps. So it's different feature maps, and we got those feature maps by applying the filter, this filter to the input image. So applying the input, this filter to the input image, and we are getting those feature maps. We have 32 features, filters, and each filter will generate a feature map. In Nest, we did that before. If you want to repeat it, it will be the same, just copy and paste. But this time, I mean, last time we used feed-forwarded neural network. This time we will use conv.net. So it will be the same. Just remember to change the input shape to 28 times 28 because times 1, because it was grayscale. Grayscale. So we need to provide height times width times number of channels. We need to define number. I covered the same code, in fact. It's conv followed by conv max pooling, conv followed by max pooling, conv. We should have, in fact, before flattening, we need to have max pooling. I mean, it's smart to have max pooling, and we will flatten. And after flatten, we will have one fully connected layer, and finally we will have a softmax layer. Right? Combine also. Model summary, plot model, train your model. So as you can see here, we got, when we use the deep learning with MNIST dataset, we are able to get much better results. So the training accuracy here is 99.7, and the validation accuracy is 99.4, right? So it's much better. As you can see here, this is a training error, training loss. It will go down all time. This is a validation loss. The validation loss is it was increasing, and after that it started to decrease, right? So anyway, you can go to this example and you can repeat this one more time. If you want to see some intermediate values, so in the same way, we need to define maybe a submodel or a base model using model API. This one will have 2 inputs and outputs. inputs equal model input, and the outputs will be the model from any layer you want to see the output. So for example, I need to see the output from layer number 4. If we need to see what is layer number 4, maybe, I don't know, in fact, maybe this is 0, 1, 2, 3, maybe 4, this one, the output from this one, which will be 3 times 3, 64. Right? It will be 3 times 3 times 64. So 64 feature maps. 64 feature maps, and each feature map will be 3 times 3. So we will go to it. As you can see here, we have 64. This one, it's 8 times 8. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8 times 8. So this one, in fact, it's 8. Oh, sorry. This one will be 8 times 8, which means we have 64 feature maps, and each feature map has a size of 3 times 3. So this one is 3 times 3, as you can see. This one is 3 times 3, as you can see. So those are the feature maps which we will get after from layer number 4, right? Layer number 4. So when the input is 2, you will get this information. You will get those feature maps. And after that, you will flatten. You will send it for the classifier to classify your problem. Yes. So if you want to practice, maybe try, for example, to go for a larger problem, which is CIFAR 10, and try to import AlexNet. Try to use AlexNet for solving this problem. AlexNet, it's a pre-trained model. Pre-trained model. And in this case, we will be using transfer learning, right? So the AlexNet, as you know, it consists of 2 parts. 1 part for feature extraction, 1 part for classification. This classification is classified into 1,000 topics or objects from 0 to maybe 999. We will import this one to my problem, and we need to add different classifier because my classification here to 100 classes. So I need to classify from 0 to 99 instead. So in this case, I will import the feature extraction part because anyway, you are working with images because AlexNet has been trained with images. So I will import that part because anyway, it will deal with raw data, which is images, and it will extract some features here, feature maps, and we will feed those feature maps to the classifier. I need to build here a new classifier. I will not use that part. I will build my own classifier. We will freeze the weights of that part, and we will train only the model. When we train the model, in this case, we will use the whole data for training only that part. Correct? And that part will not be trained because this one, it's huge. It consists of many parameters, right? So in this case, we will import the feature extraction part from AlexNet, and we will try to add. We will remove the bottom part, which is the classifier. We will use only the top part, which is the feature extraction. Add new classifier. You need to add here a new classifier. You need to decide it by yourself. Maybe 1 hidden layer, 1 output layer, it's enough. And you will use the CIFAR 10 data set for training only that part, the green part. You need to freeze the red part. And in this case, when you go back to this this model summary, you will get here total number of parameters. It will be very, very large number because we are using AlexNet, but you will get trainable parameters and the non-trainable parameters. Trainable parameters, it will be the new classifier which you added and you want to train. Non-trainable, it will be the feature extraction part which we imported from AlexNet. So this is the whole task. So thank you very much, and please let me know if you have any questions. So can you stop recording, please, Z? Z, can you stop recording?
Yes, sure.
Thank you.